Okay, good morning everyone. Welcome to this session, which is about parsing and compiling, and one other thing I've already forgotten. So we have 5 very interesting talks. My name is Stephen Kell from King's College London. I'm chairing this session. So without further ado, our first speaker is Yavor from Galwa, who's going to talk to us about DDoS safer document parsing. Take it away.
Good morning. As Stephen said, I'm Yavor and I work at Gallo, and I'm going to tell you a little bit about some work we did as a part of a bigger project funded by DARPA called SafeDocs, which aims to try and improve the situation of parsing. So why are we talking about parsing in 2024? And well, the problem is that parsers are kind of everywhere. There's pretty much no application that doesn't do some kind of parsing. And they are usually at the very kind of boundary of an application. If you're going to start attacking an application, you're going to be interacting with a parser of some sort. And furthermore, if the parser is incorrect, many exploits are based on like the parser doing something wrong. And they're not easy to get right, even though we have a whole bunch of tooling and a whole bunch of work has been done. Mistakes happen all the time. I mean, if you kind of follow security things, parsing vulnerability, if you're going to exploit a system, I was going to look at the parser first. And so as we looked at various kind of parsers, we identified roughly 3 different kind of classes of bugs in parsing code. And so the first one is just an actual implementation bug in the parser, right? That typical, there's a buffer overflow. Whoever wrote the parser didn't consider some sort of input. And then a malicious attacker gives it bad input that you're not supposed to give, and the parser, crashes or gives you access to some kind of internal data. The second very common thing is that, well, how do you know if your parser is correct? So usually there is some kind of specification, but oftentimes these things are big and are written in English, right? So there is some kind of big document that describes what the format you're parsing should do. But for this project, like for example, we were kind of interested in parsing PDF documents, and the spec for that is over 200 pages long. It's really big. And oftentimes, even though the PDF spec has been designed over years, so it is very precise, still we found things that are missing or unclear or ambiguous. So many parsing mistakes are simply because somebody misunderstood how things are supposed to work. And then what that leads to is like a mismatch, because parsers are not a standalone application. They're usually part of a bigger system. This kind of misunderstanding of the specification often leads to kind of different assumptions that the application code has and what the parser actually checked, and that's how you get exploits. Okay, and so currently there are kind of, as I said, there's been a lot of work, and in general, if you look at like regular expressions and context-free grammars, these are the things that have been studied, and the theory is very well understood. Most programming languages usually have some kind of tools to support those. So there is typically some kind of library to do regular expressions, or some kind of a tool like Bison or Yak, or in Haskell Happy, in Antler, and tools like that that would kind of take a context-free grammar and compile it for you. So oftentimes this kind of gets rid of at least the kind of bugs in the generated code, well, at least in the kind of structure of the parsing code, not in the kind of application-specific code. Typically, they all use different notations, but for these things, they're more or less the same. Usually, if you know one of them, you can kind of pick up what it means in another language. Interestingly enough, many compilers still don't seem to use those tools, and I kind of looked around, but like GCC, Clang, Rust compiler, they all come with handwritten parsers. And you kind of look around about why that is, and it's not very clear, but some seems to be concerned about efficiency, because these compilers have been developed for a long time, and even though machines are fast now, before they weren't, good error reporting is oftentimes difficult with those tools. So yeah, I don't know if anybody has more insights. I was quite surprised to find out that they don't have grammars. But however, on our project, we were more interested in processing the so-called binary formats. So these are more formats not where white space doesn't matter so much. They're more structured, more like PDF documents, Word documents, things like that. And there is a whole lot of tooling to support these tools, but there is no standard notation as far as we can tell whatsoever. The tools, oftentimes when you process binary data, are very performance oriented. So speed is what matters, and validation usually is kind of left to the application. So the job of the parser is more or less to figure out where the data is in a document, and then the application is supposed to parse it. And a lot of the tools we found kind of don't aim at parsing whole documents, but they're much more at processing like little packets, so simple struct-like structures. And when you get into more complicated whole documents, really the job is kind of split between the application and the parser, and they have some kind of a complicated sort of interaction. And so specifically these binary formats, the kind of things that make them particularly difficult for traditional parsing technologies is that they usually have a lot of data-dependent parsing. That means that you parse something from the input, and what you do next depends on what you parse. So it's not like a static structure. It is the traditional encoding of sequences is, you parse a number, and then you parse that many things. Then quite a lot of formats appear to have this non-sequential parsing. So you don't just start at the beginning of the document and go left to right the way you would parse perhaps a programming language. Instead, very often you have these kind of tricks where the objects are spread around the file or something. Sometimes they're even in a different file. And you have a table of contents kind of at the beginning that tells you where things are. So to parse things, sometimes you have to parse a little bit here, a little bit there. And obviously, that's quite different than what tools like YAC support. And finally, especially in PDF, but other tools do that, oftentimes you don't even parse the bytes in the file directly. Instead, you parse, that's kind of a form of dependent parsing, but very complicated one is like you parse the data, and maybe the data is compressed or encrypted, and then you decrypt it, and then you parse that. So you're kind of parsing input that doesn't exist, directly. Okay, so these things make it tricky, but people have written parsers like that, and I think a particularly good way to do that in languages like Haskell and in many other languages, people have written parsing combinator libraries. So these are libraries that help you write parsers by hand, but they provide a lot of common patterns, right? So you don't have to invent everything from scratch. And I kind of looked at some of the source code for big compilers, and they don't use parsing combinators. But I think that if you're going to write a parsing by hand, using something like a parsing combinator library is a very good idea. Because you at least provide some structure there. Usually they're very expressive because usually parsing combinator libraries are just embedded in a host language, and you have the full expressivity of the host language to do whatever you want. Some challenges, though, that they're non-portable. So every language has its own. Like in Haskell, we have 3 or 4. In Rust, there's GNOME or something. For C, there's Hammer. But yeah, they look nothing alike. I mean, you recognize some kind of functions. And also, they're pretty difficult to analyze because analyzing the parser amounts to kind of analyzing basically an arbitrary program embedded in a general purpose language. And reasoning about those is hard because they are supposed to do very many things. And finally, depending on the parsing library, oftentimes you see this kind of mixing of what's parsing and what's application logic because you're just writing a program. I find that in Haskell that is generally a little bit better because we have monads and whatnot, so you can see at least what's parsing code and what's not parsing code. But when you go to languages like Rust or C, it really kind of gets pretty mixed up usually. And so this kind of leads to our idea, the way we kind of thought to approach this problem of parsing document formats is we decided to kind of abstract this idea of parsing combinator into a standalone parsing DSL that we call Daedalus. Okay, and the focus of Daedalus, the idea was that we can use it as a specification language for specifying binary formats. So the hope, if Daedalus gets picked up, is that when you kind of define a new binary format, you can provide a Daedalus specification that should be a lot more formal than just writing it by hand. So Daedalus should be readable, importantly. The design, it is very much inspired by parsing combinators in Haskell. So if you've seen those, the things here should be pretty familiar. But because it's a domain-specific language, we've added a whole lot of patterns that are just convenient, some nice notation. It is not as general as Haskell. It's a much simpler language, but it is based on a purely functional programming language. And the idea is that also we provide backends that compile Daedalus specifications to efficient code. So I'll tell you a little bit more about that. But at the moment, we have two backends, one to C++, one to Haskell. And we hope to add more, specifically Rust next. So let me give you a flavor of what Daedalus is. So Daedalus, as I said, it's inspired by Haskell. So it basically contains two sub-languages, you can think of it, that share a common syntax. The one is an effectful language of parsing. That's kind of when you specify a grammar and you say parse this thing, then parse this thing, then parse this thing. And then it has a purely functional computation language for constructing semantic values. So what a semantic value is the result of a parser, basically. You can think of it as the parse tree or the representation of your packet, something like that. And so with data-dependent languages, you need to, like with tools like Antler or Bison, they don't support data-dependent language, and because of that, the semantic values are built in the host language, right? You write your grammar, and then you say, when you match this through, this is what you do. Here we have to do this part in the language because you can depend on it. So the grammar needs to be able to understand the values you parse so that you can make dependent decisions. The language itself is pretty standard. We try to not innovate there at all. So it has a Hindley-Milner-based type system with qualified types, much like Haskell, a lot simpler than Haskell because there's no general type classes. We just have built-in classes. Supports polymorphism and type inference. It's all statically typed. And the type system explicitly keeps track of this kind of, this is a parser, this is not a parser, and you can't mix them. Also, it's extensible in the sense that we have a foreign function interface. We found that in practice, this is really important to have because, as I said, these formats oftentimes, for example, require you to do decryption. And we didn't want to implement the decryption algorithm in the parser. There's already standard libraries to do that. But while you're parsing, you need to call into this library. And so yeah, we have a foreign function interface. OK. So this is what the Daedalus declaration looks like. It is pretty simple. The def is a keyword there that says we're defining a parser. The way you know it's a parser is we have a syntactic convention. The parsers start with the capital letters. Block means we are sequencing. It is very similar to the do notation in Haskell. Let h equals header means run the parser header and name the result h. And then perhaps not surprising, body h means parse the body. That's another parser, but this parser now depends on the value, right? So how you parse the body would depend typically on what's in the header. So that's a very common pattern. And then you define header and body in some way. So this kind of having essentially, if you will, grammar productions parameterized by value is how we get data dependence. So if you're familiar with monads, this is your standard monadic parser. One thing that is interesting is the Daedalus is not exactly monadic. I mean, certainly it has things like bind, like this block thing is sequential, and we have parse the empty thing, which would be pure return in a monad. And parsers may be parameterized by both values and other parsers. So you can have productions that are parameterized by other productions. So you can define part a list of x, where x is another parser. What we don't support is parsers that return other parsers. So parsers can only return semantic values. So there is kind of a strict distinction between values and parsers. And if you will, the type of parsers is of kind value to parser. And that does not allow you to type things like the join operation, which is the mathematical definition of a monad has this, requires a parser that returns a parser and flattens it. You cannot express that in Daedalus. It's kind of an interesting construct that I'd like to spend more work in the future studying. It's a kind of first order monad and seems to be somewhat related to this work on call by push value. If somebody has ideas, I'd be happy to talk to you afterwards. And it is very convenient because it makes code easier to compile, but also enables us to have this kind of applicative notation where instead of having to explicitly sequence things, we allow you to write things in an expression form. And based on context, the program would automatically know, OK, body expects a value, but it's been given a parser here, so I'm going to sequence them for you implicitly. In this way, you get a lot of grammars that you avoid naming intermediate values that are kind of used one time. It's pretty natural if you're used to kind of working in an imperative language to mix these pure and effectful things. Here, we allow you to do that, but we are still tracking that you don't make mistakes. As another little example of what a simple dataless specification looks like, we have this a lot of iteration constructs, but one of them is this many construct. And by the way, in this code, I make use of this kind of syntactic sugar for mixing parsers a lot. To parse a number in base 10, many is a loop, you can think of it, that is stateful. It has a piece of state called n there. And the body of a loop can mention the state n, and will compute the new value for n. And you kind of apply the body of a loop until it fails. So the body of a loop is a parser here. So to parse a digit, you first parse one digit, and that's your initial state. And then to parse the next digit, you multiply by 10, and you add one more digit. And this is how you parse base 10 numbers. And you can easily see how to generalize that to other bases. To parse a digit, we have some special notation. So we support character classes and things like that. We support casting. So when you match bytes, you by default get a byte. We have a notion of a byte, but dataless know that it's safe to turn a byte to an int. It would complain if you try to turn an int to a byte, but we also support dynamic checks to do that. So this is not, like if you're interested in dataless, there's more details in the paper, and we have a user manual and a tutorial and whatnot. So this is supposed to give you a flavor of the language. How am I doing on type? OK, we also support, we have a bunch of primitives for stream manipulation. So as I said, oftentimes you need to parse code that is non-sequential or even code that is produced as a computation. So we expose basically the input stream directly to the user. Basically, stream inputs are a first-class value. They're a normal value just like integers or booleans and whatnot. And you can store them in your parsing input if you want to have some stuff that's unparsed and you want to parse it later. Or if you want to code to the application to decrypt something and then change the input to the result. So by default, this is pretty low level. And if you use this a lot, leads to parsers that are very confusing to analyze. So we try to use it very sparingly. Excuse me. And we opt instead for, in our standard library, we kind of have a bunch of patterns that we have identified. For example, chunk NP is a common pattern that it's a little bit like I want to parse a token that is the next 10 bytes processed with P. And it will kind of advance the input by n bytes. And it will fail if there's not n bytes and so on. Dataless has a lot. OK, I'll wrap up. It has a whole bunch of other features. Check, cast, whatever, that these are described in the paper. We have a compiler for dataless, which is pretty efficient. And the compiler has, as I mentioned, 2 backends for C++ and Haskell. We have a couple of other tools that analyze the dataless grammars and can kind of detect cavities in documents. So the benefit of having a standalone language is that you can analyze it a lot easier. We did some evaluation, and our parsers, our compiler is pretty fast. It seems to be a bit faster than a bunch of, on these simple examples anyway, other tools. I wouldn't take that as being great, but the point is here that the generated code, so the thing in brackets there is the parsing in megabytes per second. So we are faster than all of those things, but you know, on these little examples, in general, we are, I expect, in the same kind of ballpark as other tools. Yeah, so the performance is good for both the C++ and the Haskell backend. And I think that's pretty much it. In summary, I wanted to say that processing binary files is difficult, and parsing combinators, I think, are a good way to deal with these very kind of exotic formats. But it is good to have a language that is not language independent, like a language that is specific to the parsing. And purely functional languages are good for that. And hopefully, Daedalus can serve this person. We have an efficient compiler for it. And yes, as I said, we're still working on it. We're hoping to add a new backend for Rust soon. If you're interested to learn more about it, the repository is it's all open source. It's on our GitHub, and documentation is all at this URL as well. There is a user manual for the language and tutorial. And I'd be happy to take any questions.
Great, thank you very much. Let's thank Java for the talk. While our next speaker sets up, we have time for maybe one quick question if someone wants to run to the mic. Anyone can see some movement? No one is running to the mic. I have a quick question, Javor. So is there any way for people to adopt this gradually? Like say they've got a big program that's using an existing parser that they wrote. Is there a story for somehow how to migrate to using Daedalus?
Yeah, you can. Daedalus just generate, for example, the C++ backend. You can write a bit of parser and to generate some C++ classes for you. So if you want part of the parser to be written in Daedalus and the rest to be written manually, you can totally do that. Yeah, how you structure it, it's yourself. It's up to you, yeah.
Okay, great. Thank you very much. Let's thank the speaker again.
Yeah.
So our next speaker is Avery from the University of Toronto, talking about, I'll let you pronounce the first word because I don't know how it's pronounced, but translation of sparse codes using equivalences. Take it away, Avery.
Thanks. Yes, thank you. My name's Avery, and I'm excited to be presenting our work spec. So that's how you say it. You say spec. And yes, so this is a joint work between Toronto and folks at Microsoft Research. And because this is a bit of a sparse-heavy talk, I just want to first make sure we're all on the same page about sparsity. So on the upper left-hand corner, there's some C source code that's implementing multiplication between a dense matrix and a dense vector. And this is a picture just to give you an intuition of what's going on. And in a lot of applications, most of these entries in the matrix might be 0, and that's what you'd call a sparse matrix. So because we're doing like just additions and multiplications, most of the time, the zeros aren't going to affect the computation at all. So it'd be much more efficient for space and for computation if we just toss those zeros away and only store the non-zeros. So one way to do that is go row by row and collect all of the non-zero elements and smush them together in their own matrix. There's many ways to compress these matrices, and they're all called storage formats. So this is an example storage format that has an additional array to tell us like where each row starts and begins, and a third one to also tell us what are the column index of each array. And the details are not important. The important thing is that now it has a big effect on how the source code implements this multiplication, because now it's using these sparse structures that are extremely difficult for a general purpose compiler to optimize if it doesn't know anything about what the code is doing. And the important detail is that these kind of sparse codes are hand-implemented and handwritten in a lot of important programs, in particular like legacy programs. And to go through those code bases and manually rewrite them to something more modern is very tedious and very error-prone. So what we'd like to do, our goal is to take these kind of general codes as input, so we don't assume anything about these codes, and be able to automatically translate them into like a high-performance library or a DSL. So in this case, we're offloading the computation of the sparse matrix vector multiply onto GPU by making some kusparse calls. And importantly, to ensure the correctness of the translation, we also have to assert some preconditions at runtime. And I'll tell more detail about these later in the talk. But first, I just want to give an overview of the total end-to-end pipeline. So spec operates on LLVM IR, and we do some analysis statically to try to detect what storage formats are used inside of the code. And if we do detect sparsity, then we have a pathway to make sure that our guesses were correct. But even though spec is designed to target sparse codes, like to handle sparse codes, there's another path through the pipeline, which is if there isn't any sparsity detected, we can still handle any dense codes. And after some magic in the module that I will explain later in the slide, then we can perform this translation, and that enables very high speedups, which should not be surprising because, as I said before, these are high-performance libraries that are specifically designed for this purpose. So that itself should not be surprising, but here I just want to illustrate what's possible once you step out of trying to force the general purpose compiler to do something and shift it onto special purpose application. So now I'll go step by step through the pipeline. And in the first stage, we take the LLVM IR, and we want to analyze it to try and detect all of the sparse structures that might exist inside of the program. And even though this is LLVM IR, I'm going to write it as source code so we don't all have to try to parse LLVM IR. And the first step is we generate a graph that represents the relationships between variables in the program where they're defined and where they're used. So the way to read this graph is there's some j in the program that ranges over 0 to m, and the arrow is used to indicate that j is used in this expression, row j plus 1, and that expression itself defines some new variable k and so on. So this is the way to interpret this graph. And the crucial insight is that we can generate like this concrete graph from the input code, but at the same time, any code using a particular sparse structure, it should contain a graph that's characteristic of that format. So in this case, we know, for example, any code that's using this particular compressed sparse row format, it should have a graph that looks like this. We don't care exactly what v1 is or v2 or so on. Those are kind of placeholder variables. We just know that this general structure should be found in a code that uses CSR. So if we can construct a correspondence between the two graphs, then that gives us a good indication that this structure probably is being used in the program. But of course, that is just a guess. So there's many things that could go wrong, and the two main issues that pose to correctness is firstly that the input program contains all of the right structures, like it contains all of the right relationships between variables to make it look like it's using a certain sparse structure, but at runtime, the input data is doing something different. So this picture is showing an example of something that looks like a sparse structure, but actually the input data inside does not represent a sparse matrix anymore. So the source code will look exactly the same as another source code doing a sparse matrix vector multiply, but the semantics are totally different. So to blindly do a translation, in this case, is actually a bug. It's not correct. So we have to have a way to make sure this doesn't happen. And the second case is that maybe there are some structures that spec doesn't know about or that it missed. So we have to make sure that we actually caught all of the behavior of the sparse structure. OK. So the way that's done is through inequivalence check. And it's a little bit complicated, so I'll give a very high-level overview here, and there's like all the details about it in the paper. But the main intuition is that we start with some input code, and we made some guesses about what sparsity is inside of the code. And based off that guess, we should be able to undo the sparsity. We should be able to symbolically reconstruct a dense version from the sparse version. And if we made all the right guesses, then we should be able to prove that these two program versions are the same program. Just one is sparse and one is dense. So that gives us a certainty that we caught all of the sparse structures, and it also gives us the preconditions we need at runtime to check to make sure like the input data is actually representing a sparse matrix. And the way this equivalence check is done is by constructing a joint transition system. So I'll show an example right now. On the left-hand side, I'm showing two iterations of computing a dot product between the first row of the matrix and the input vector. There's two elements, 1 and 1, multiplying by two elements, P2 and P3. And there are two possible cases that can happen in this joint transition system. So this is showing the first case where both program versions are operating on the same non-zeros at the same time. So that's shown by these 4 different states. On the left-hand side, there's the first state. Then it takes one step. It multiplies 1 times P3 and accumulates back to the result. So that gives you the successor state. And these both systems are related, shown by the red dashed line. In other words, they are equivalent under our notion of equivalence. And that's easy to just like eyeball because 1 times P2 plus 1 times P3 is the same both sides. Okay, so that's one possibility. But if you look at the format-free code, we have 1, 1, and then now we have a 0 next. But we have no zeros in the input code. So this is the second possibility that can happen, is that now the dense version of the code, the format-free version, takes a step. In other words, it computes on the 0 element, but the input code does not store the 0 element. It skips it. So now we have to relate this extra state, 1 times P2 plus 1 times P3 plus 0 times P4, to this other state in the input version. So again, this is like easy to eyeball since 0 times anything is 0, and it should be the same. And that equivalence relation is shown, again, with the red dashed line. And in by simulation notions, this is stuttering by simulation relation. Okay. So if the equivalence check succeeds, then we know all of the sparse structures that are occurring in the program. But that doesn't tell us anything about what the program is doing. We don't know anything about the computation. We just know how the data is stored. So we still need to like give a name to this computation. And it now doesn't have any sparse structures, which makes it a bit easier. And the way this is done is we have a database of reference implementations that are just written in a straightforward way. Like, for example, the GEMV, the general matrix vector multiplication reference implementation is 2 for loops of C code, and that's it. We have these database of reference implementations, and we want to prove which versions of the reference implementation are equivalent to the input code. So what we do that by generating a bunch of rewrite rules, like one rewrite rule for each reference implementation. You give us a reference implementation in some source code that can be compiled to LLVM-IR, and we can automatically generate a rewrite rule where the left-hand side is the function body of the reference implementation, where the arguments are replaced with placeholder variables that can match any term. And the right-hand side is just basically a semantic label. It's just saying, OK, this big bundle of terms can actually just be called this other thing, and we know the semantics of this thing. Okay, so this is a way to just name all of the different segments of the input program. And in addition, we also have some like generic rewrite rules like on arithmetic and also some loop transformations. So then the next step is we take the format-free code where we pulled out all of the sparsity, and we represent it as a term in an E-graph. And this is basically represented as where loops are represented as folds, functional folds, and the folds will have lambdas inside to capture the loop body, and it's all defined recursively so that everything will be like a fold or a captured lambda. Okay. So now we have our term in an E-graph, and this term is able to E-match successfully on the rewrite rule that we generated from the reference implementation. And what that allows is the term and the gemv function symbol to be placed in the same equivalence class. They are proven to be congruent, which means that we know that they're equivalent. So now we've been able to assign a name to the computation that the input code is doing. We know that it's a gemv, and we know the meaning behind its different parameters, like y, beta, alpha, and so on. So then the final step is we have a name for the computation. It's doing a matrix vector multiply. We know the storage formats and what variables they're operating on. And so it's basically a lookup table, like gemv plus CSR. You can just look up the library and say, OK, that's going to be SPMV with CSR, and so on. So the translation step is very straightforward. We just look to see what semantics there are and what formats there are and what library calls are available to us. And we evaluated spec across 10 different benchmarks. So some of these are SPMV, some are gem, some are histogram and reduction. So it's a mixture of sparse and dense codes. And the takeaway here is that the cost of the runtime check is quite low. And the benefit from offloading to optimized implementations is quite significant. Additionally, we compared against other tools that try to match semantics, and we were the one that was able to do it correctly and over the most number of cases. And finally, even though the whole tool is basically a Python implementation, we're mostly on par with LLVM's 03 pipeline. So the latency here, compared to like lots of other equivalence checking tools, is quite low. So yeah, this is spec. The main idea here is to be able to easily identify segments of input code that you care about, map them to nice, efficient implementations, and we have support for sparsity built in. The artifacts are available online, and there's a README about how to add your own reference implementations for code you care about, how to add your own backends. So please feel free to download it and try it out and let me know. And yeah, that's everything I wanted to say. So thank you.
Thank you. We have time for 1 or 2 questions, if anyone would like to head up to the mic.
Yeah, there was one claim on a particular slide where you said that there are 2 problems that are solved by the equivalence checking. And the latter of those 2 problems was missing a format. And I just didn't get that claim because you've got some library of formats, and you've got a false negative if you just don't recognize a given format. In fact, we're already down the branch of the flowchart that said, yes, we recognize the format. So if we fail to miss a format, how is this correctness issue handled helped by the stuttering by simulation?
OK, sure, good question. So basically, what would happen is when we tried to construct the format-free code, there would still be some potentially sparse, or not even sparse, but just certain data structures that we can't reason about. We'd fail to construct a strong enough relation between the 2 systems, and the bisimulation would fail. Yeah.
Thanks.
It seemed when you encoded your programs into egglog, you used binders in your language?
Here, yes.
Yeah. I guess it's kind of a suggestive question. How did you not run into problems with this?
Yes, so I've talked to the egglog people a lot about this because, yeah, this is a well-known problem. The important distinction is that we do not implement a lambda calculus in the eGraph. We don't. The lambda is just used for capturing term names, and that's it. Yeah. So we never do any manipulations on the binders.
Oh, okay.
Yeah.
Cool, thanks.
Maybe when while our next speaker is setting up, we could have one more question if anyone has one. I've got a very quick question, actually. So the very early part of your pipeline was basically detecting the sparseness of patterns, and you said it sometimes goes wrong.
Mm-hmm.
Is it useful to make human beings tell you what pattern they think their code is using?
Yeah, so you can also add your own graphs. Basically, we have the ability to, like, you can have a callback function that gets triggered in the LLVM static analysis, where you can do your own search through the IR. But that's, you know, if you're familiar with LLVM,
Okay.
it's a bit tricky to
Expert
do.
task.
Yeah.
Got it. Okay. Thank you very much.
Okay.
Let's thank our speaker again. I'm going to just quickly grab the question mic because we have a double act in the next talk, and I have to do a quick. Okay, Severia's gone for it. He's on it. Brilliant. That's wonderful. So our next speakers, we have two of them. We have Severio and Marco from different institutions. I'll let you introduce yourselves. Yep. And this is a top-class paper, so it's about choral object-oriented choreographic programming. Take it away.
Hi, I'm Saverio from the University of Bologna, and I'm a member of the INRIA OLES team. And this is joint work with Marco Peresotti and Fabrizio Montesi from the University of Southern Denmark. And we split the presentation both because we are both here, but because one introduces choreographic programming, since this is, we think, the first time choreographic programming goes mainstream. So we introduce choreographic programming here, then of course all of you will know it, and nobody needs to introduce that anymore. And then we will talk, of course, about choral. I will leave the floor to Marco. So let's start from the context where choreographic programming was born, that of concurrent and distributed systems. And programming correctly distributed systems is hard, distributed and concurrent systems. And the problem is we have in mind a specification, and usually we use these kind of schemas to represent those. So you have, let's see if this works, you have participants that are also called roles in choreographies, and then they exchange messages. So they interact through messages and they exchange data. And it's simple to see what happens in this protocol. We have C sending some credentials and then a branching behavior that is distributed where A checks the validity of the credentials and then sends OK or a KO to WS, which sends either a valid token or an empty one. So it's pretty straightforward to see what happens. But then if you look at the implementation there on the right, you see that it's not so easy to check that the implementation is actually doing what the specification does. And if I hid the specification, it would be probably even harder to understand what happens in the distributed system just by looking at the single endpoints. They are also called the implementations separated. So, and we know that even debugging the stuff and finding, so making sure that we correctly implemented the protocol and debugging the implementation, finding the bugs due to concurrency is difficult due to non-determinism, right, and the state explosion problem. So the idea of choreographic programming is we have already the schematics. Why don't we start from there and then let a compiler do the job of implementing correctly the distributed system? So what we do is that we give a artifact that is closer to a programming language to the programmers so that they can express the local computations, the general transitions in the system, the interactions in the system. So you have something like this where you can say, I have a role, C that has some value. This value is stored under the variable credential, which is local to C, and then an interaction that transmits that information to A, which stores that information under X. So given this information, we can compile the general schematics into the implementation in a correct way meaning that we have theorems saying whatever the choreography says, the implementation does, and the implementation cannot do more than what the choreography says. And this is what we normally call the choreography compliance guarantee. So we don't have surprises. And the corollaries are really communication safety, so there is nothing unexpected by one of the members done by some other participants. And we don't have deadlocks on messages. And this is simply because we have this interaction that says this is a send and a reception that are always paired. So you can never write syntactically a send that is unmatched by a reception. So the foundations are pretty much there. It's been, let's say, 12, 15 years we've been working on the paradigm. So the question we asked with Coral is this paradigm ready so that we can bring it to the mainstream? And to answer this question, we wondered if we could merge a mainstream modular way of building software in the large to choreographic programming. And the idea with Coral was, okay, let's try to do that with object orientation. It's widespread, it's working, so why not using that? And by marrying choreographic programming with object orientation, we actually found that we have new understandings of what is abstraction, encapsulation, polymorphisms, because we are elevating those at the level of choreography, so at the level of the distributed system. And the additional interesting point is, and that was explicit, of course, we modeled Coral as close as possible to Java so that it feels like Java and you can interact with Java programming. You can import Java libraries in Coral and bring them up to the choreographic level, but you can also have, and this is the next slide, you can also have classes that are at the choreographic level that you can compile down to Java classes and you can use in your local code. So that now you have local code that can take part in a choreography and in other choreographies too. So you have this double interpretation. And then I can leave the floor to Marco for more on Coral.
Thanks. So how we came up with the design of Coral. The first thing we needed to do was essentially looking at the primitive for communication, that is the core of choreographic programming, and interpret it or understand what would be its equivalent in object-oriented programming. Here we see on the left what has been happening traditionally in choreographic programming until Coral. And communication is expressed with this arrow primitive. It means process P evaluates an expression E, sends the result to Q, that will store it under variable X. This is a primitive of the language, it's a statement, and syntactically combine the sending and receiving, as Saverio said. When moving to an object-oriented setting, we instead moved from a primitive to a method invocation, and we leverage the properties of object orientation in order to avoid fixing an implementation. This is no longer a primitive, it's just a method invocation. It's one of the main objectives we had with Coral. We wanted to avoid fixing and committing on a middleware. The other main difference is that in the traditionally, the placement of data and placement of computation, for instance, evaluating this expression, has been made manifest at the level of syntax with these prefixes. You needed to annotate every single variable, piece of data, and et cetera. Instead, with Coral, we leverage the rich type system of the object-oriented language in order to express this property. This allows to get a syntax that is a little bit more similar to essentially programming in Java. Thanks to this new type system that allows to track data placement. For instance, here we have this expression is meaning that we have an integer that is located at A, so a process or a participant A. Thanks to this interpretation, then communication or a channel could be any object that has a method that allows to take data located at A and returns data of the same local type located at B, like anything with a signature like this one, for instance. Then we expect from the realization of this in the local code, so the endpoints, to have essentially two objects that offer a method with these signatures. So for the sender, for A, we expect to be able to provide an integer or the payload of the message, get nothing out of it. On the other side, we want to just get the result. So essentially a send and a receive. Now, this means that this kind of method needs to be offered by an object or a type that is distributed across two roles, A and B, but they are combined in a single artifact. Then when we compile it, we will get, again, a definition for the sender, a definition for the receiver. But what is important for us is this is just an ordinary interface in Coral. It's not a primitive, there's nothing special about it. And this means we don't need to commit on any specific implementation. In the standard library of Coral, we have some default implementation, leverage, I don't know, TLS channels, various methods of serialization. You will find many examples in the paper and on the website. It also allows us to leverage the object-oriented principles of encapsulation, polymorphism, subtyping. We have a hierarchy of these interfaces that allows you to express different capabilities. I want to have a bidirectional channel, there is an interface for that. I want to have, I don't know, a broadcasting channel, there is an interface for that. And allows you to decouple, again, specifying what are your capabilities and what are the implementation details. Now, interesting thing is that now we have these types that can be distributed. They can talk about multiple roles and participants. And here is an example to give you a taste of Coral. It's a replicated cell. So we have this class, and I will walk you through the details while we compile it. We have this class distributed across two participants, Alice and Bob. And here on the right, we have the implementation for Alice. So we just get a simple class for Alice. We're using the underscore for the role. And then here we will have Alice has a private field of an integer located at Alice, so that will be projected to a field for Alice. Bob has an equivalent field, will not be see anything for Alice. They share a channel in order to share updates to these replicated data. And for that, they have a specific channel. Then methods. Here we have an example, a method for that allows Alice to update its value at this line, and then communicating the value to Bob that will update its field. Again, this will become just a send for Alice and symmetrically a receive for Bob. The interesting thing here is that the design of Coral allows you to control the API. Here, by looking at the API at the choreographic level, you can already understand what the API for the implemented code will look like. And here we have the symmetric case. So we ran some evaluation in the paper. This was a simple example. There are more in the papers running from the choreographic equivalent of Hello World with just a couple of lines of code to more complicated distributed authentication protocols with, I don't know, 5 participants. And what is, for us, the most interesting metric is how much code we can save. So we run from a gain of 55% in terms of size increase to almost 400%. This is code that compiler is generating for us. We avoid much of these exponential explosion in terms of possible combinations we don't need to check. We also made another evaluation doing an architectural refactoring. We started from an existing application, an open source microblogging platform based on Java service pages and Redis. And we wanted to create a distributed version, essentially moving from a monolith implementation to a microservice. We use Coral for programming the interaction. Everything else, logic, data structure, etc., we lifted from the existing code, Java code. And what we gained was essentially a drop-in replacement. It was not so complicated to get essentially to a distributed implementation. There is way more in the paper, but essentially what we achieved is a language for programming distributed system that brought modularity and object orientation to choreographic programming, moving it beyond just the community of concurrency theory. Is fully interoperable with a mainstream language, Java. And in the paper, you will find that the compilation is fully specified. There are more details for the evaluation. For instance, we did a comparison with Akka and Java. And you will find more details about the development methodology. What should go in the choreography? What should stay in choreographic code, especially for error handling? And since now we have this dimension of choreographic code, we also started wondering, how do we test this distributed system? We have a way of specifying tests from a global perspective of our choreographies. And so we had a kind of choreographic JUnit, if you want. And the other thing I want to point out is that the first release of Coral happened in 2020. Since then, we've seen that many of the ideas developed with Coral started popping up in other languages. There has been work on Haskell by Lindsay team. There has been, I think, 2 already implementation bringing these ideas to Rust. So this sparkled kind of an explosion, bringing choreographic programming to the PL community. So thank you, everybody, for your attention.
Thank you very much. We have lots of time for questions. If anyone would like to head to the mic, and we even have a mic now. Thank you very much. Just in time, mic placement.
Okay, thank you very much for the nice talk. Can you hear me, actually? Maybe I have to do it this way. Yeah. That's. I have one question, and suppose you have 2 channels, and they share either the sending side or the receiving side.
Yeah.
What's going to happen?
Well, depends on the implementation of the channel. But if there is any interference, like, I don't know, you have 2 objects that represent 2 channels, but you're sharing a socket, then the compiler cannot give you any guarantee there. So instantiating the choreographies and setting up the channels is, in a way, outside of the language. But the moment you can have multiple channels between the same participants. So for us, it's just an object there. I could have, I don't know, 3 channels between Alice and Bob because one is encrypted, the other one is in clear.
No, I mean 2 channels that really have the same endpoint or the same starting point. Do you rule this out? Do you have a compiler check for this?
So like one sender and 2 different receivers?
Yeah.
No, it's possible and it's not an issue.
What do you do then? Broadcast?
Sorry?
Do you broadcast then?
No, there are 2 separate channels with their own implementation.
Okay.
Yeah.
Okay.
But we have examples in the library of channels for broadcasting, but in that case, they are specified as an object that involves a sender and, I don't know, 5 receivers.
Yeah, I meant rather if you write it like this.
Yeah.
But I think we should probably take it offline.
Okay.
Thank you for the talk, very interesting. I was wondering about error handling and exceptions. Yeah, like, because if you throw an exception and it's something that's getting compiled to 2 different files and 2 different machines, so how do you approach error handling?
That's a super interesting question because, I mean, in general, error handling, I think, is not a solved problem for choreographic programming in general. There is a lot of active research there. We are still brainstorming about what could be a good solution. Coral has an exception mechanism, but those are local exceptions. So for that, much of the work relies on the programmer. So up to the point these are local exceptions, they can be handled, but we don't have a mechanism for distributed exceptions because we don't assume a middleware. Of course, one could have rely on some libraries in order to coordinate this. And for instance, if you work on the theoretical works on choreographic programming, multi-party session types, the moment they start dealing with exceptions or user-generated errors, they assume some form of reliable communication in order to handle coordination. What we discuss in the paper, especially in relation to the development methodology, is if errors or exceptions are part of the protocol, then they need to be handled at the choreographic level. If these are, let's say, non-recoverable exceptions from the perspective of the protocol, then at the moment, these are just going to pop up to the invoker of the choreography, and at that point, we are out of what we can handle at the moment.
Thank you.
We have time for one more, I think.
Very energetic talk, thank you. My name is Krishna Nandioda from IIT Madras. I had a question related to the programmer's view of this. Typically, we like to, for large applications, independent parts separately, because it's easy to write the code, easy to maintain the code. And now you are proposing, hey, let's mash up everything together, right? Your thoughts on that? Thank you.
Not everything, but the communication part. So the idea, also, the origin of the name is choreographies as a library. That's the AL. Usually, I mean, you can program an entire application in Coral. I'm not going to stop you. But especially in order to maintain this modularity of code and et cetera, the idea would be you use the choreographic language, the choreographic level, to program the interactions. But for the local logics of your endpoints, that you rely on your language or technology that you prefer. Because then, I mean, it's how many things happen. You just release the communication library, like giving an endpoint client in order to access your cloud API. So this is more or less what we suggest.
We can squeeze in one more question while the next speaker sets up.
Okay, yeah, thank you for the interesting talk. Just a quick thing. I think it's related to a couple of the other questions, and that is, as I see it, the main sort of design contribution that you made was to abstract over the communication, the implementation of the communication protocol, right? So have you thought about what correctness requirements that communication has to satisfy? You know, like if I go and implement my own communication primitives for some particular platform, implementation platform, what are the requirements that my implementation has to satisfy?
Okay. So right now, for the channels you will find in the standard library of Coral, the assumption is essentially this is a reliable channel, which is a high asking. Under that very high assumption, then this is data-free, everything works, of course. There are libraries offered with Coral, and Dan Plugin worked on one of those that offer you a different channel API that allows you to handle errors, program asynchronously on channels, and then, of course, I mean, it depends on the kind of implementation you want to pick. And the compiler is, I mean, you don't even need to touch the compiler. You just need to plug in the library of your choosing.
Great. In 1 second, we're going to thank our speaker again. I'm going to suggest that because there's an accumulation of people near the door, there's lots of seats over this side. So if you want to come around the front and just fill up those seats, and we'll applaud our speakers again. Thank you very much.
Thanks. Oh, thank you. I was running away with your microphone.
Okay, great. So let's continue. Our next speaker is Dorian, and he's going to be talking to us about compiling with abstract interpretation. Take it away.
Is that better? Yeah. Yes. Okay, sorry. As I was saying, I'm going to present you the work of compiling with abstract interpretation, which is work I did with my PhD supervisor, Mathieu Lemaire. And so what we mean by compiling with abstract interpretation is both using an abstract interpretation framework to perform compilation, and then using that compilation result to improve the analysis performed by abstract interpretation. You see, we have this interplay between program analysis and transformations where they can be mutually beneficial. Some transformations help make programs easier to analyze. So a very small example, if you rewrite an expression e plus e into 2 times e, then it becomes easier to prove that e is even. But on the other hand, prior analysis is necessary for some program transformation. A good example is dead code elimination. If you want to remove a code that is never executed, then you need to prove that that code is indeed never executed. And so abstract interpretation comes in here because it's a good framework to combine multiple analysis together and combine them in such a way that they collaborate and they get more precision than they would have if they were executed sequentially. And so the question we were asking is, could you also do transformations with abstract interpretation and so have this benefit directly into an abstract interpretation instead of requiring prior transformations before your analysis. And so the key ideas of our paper, first of all, was to use some free algebra domains, which are just term domains, which encode each of our domain constructors with a domain functions with a different constructor. And using these, it's actually fairly easy to generate a new program as a result of an abstract interpretation analysis. The next step is what we call domain functors, which are just functions that take in a domain and yield a new slightly modified domain. And these can very easily encode small compilation passes. And what we noticed is that soundness and completeness of these functors is related to forward and backward simulations between the source and generated program. And finally, we focused more closely to compilation to an SSI form because, well, SSA appeared in compilation as an intermediate representation because it's fairly easy to analyze and transform. And using SSA, we were in fact able to get fairly simple non-relational domains which were nonetheless more precise than what you'd have before compilation. So before presenting the free algebra domains, I'll quickly explain how our abstract interpretation framework works. So the idea is here you have a very small example program, which is just represented as a control flow graph. And then you have two types of edges on this graph. You have assignment edges, which change the value of a variable, and you have conditional edges, which are only taken if a guard is true. And so the concrete state of your program is, well, here we just have three variables, so it's the numeric state of the three variables and the current control flow point you are at. In abstract interpretation, what we want is an abstract state. So for example, a classical abstract domain is to, instead of having an exact numeric value for each variable, you have an interval of possible values. But really, from the abstract interpreter, this state can be opaque. So it's just going to be an opaque type for us. And to perform the analysis, what we need? Well, we need an entry point, which is the abstraction of the state at the start of the program. And then after taking an edge, we need to be able to refine the state. So this is the role of the apply function. It just takes the state at the previous point, the relation of the edge, and just yields a new abstraction of the state at 1. And with that, we can start propagating happily along the program. When we reach point 4, we realize we need a new function because point 4 doesn't have one ancestor, it has two. So we need a join function so that we can, which is essentially a union of abstract states, which gives us the best abstraction we can have here. And finally, just doing this all along the program, we have no guarantee that our analysis will eventually terminate, which is why we need the loss operator, which is a widening operator. And what the widening does is, if applied repeatedly, it's here to guarantee that we will eventually reach the fixed point. So now we have all the operations we need to analyze the program fully. I didn't show the rest of the analysis, but you just keep propagating in the loop until you reach a fixed point, and then you propagate beyond the loop. And so whenever you have an interface like this with a type and a bunch of functions that manipulate the type, you can encode it as what we call a free algebra, but it's essentially your type is going to be terms which each correspond to one of the functions. So you'd have one constructor with function. They have the exact same signature with the exception of the widening, because as I mentioned, the goal of the widening is to break loops. And if it keeps its arguments, it's just going to grow, and ensure the opposite, that loops never converge. So the widening just forgets its arguments and only remembers a unique identifier. And with these terms, when we yield our analysis, we'll have at each program point a new term, which is one of these constructors. And with these, we can actually recreate the program graph. So if we look at the apply constructor, which matches the apply function, well, we use the apply function in the analysis on edges, so the apply naturally maps to a very simple edge. The join constructor, well, the join was used when we had multiple edges coming to a point. So we just take all the edges that come into the point that appear in the set, that's the join's argument, and we have the join inherit those edges. And for the lock, that's where we need to unfold the widening, recover the pre-widening term, which is going to be a join, and then use the two previous rules. And with that, we can generate a graph of ancestors of a given term. And if we use that in our analysis, what we notice is that we get a new graph isomorphism. Essentially, analyzing with this free algebra domain gives you the same program graph. You just renamed all the control flow locations to your free algebra terms. So right now, that sounds a bit useless because we've used a very big analysis just to get something we already had. But already, you could use tools from abstract interpretation, like a product with a numerical domain, to perform simple dead code elimination and some very basic transformations. But if you want to do bigger transformation, that's where we'll need the next tool we use, which are functors. So I mentioned a functor is just a function that takes a domain and yields a new domain. In particular, we're going to be mostly interested in some that copy most of stuff from the initial domain. They don't change the state, the entry point, the join, or the widening, but they do change the apply function. And essentially, in the apply, the functor can inspect the state. It can inspect the relation being applied and decide to make changes to what it's going to apply. So for a very simple example, we have a functor that can simplify conditionals. And so what this does is whenever you're applying a conditional expression, it's going to see if the underlying domain can know something about the expression E. So for instance, if we can prove that in state T, E is always false, then we can just return bottom because we're assuming false. Conversely, if we can prove that E is always true, we can remove the assumption. And if we cannot prove that E is true or false in state T, then we keep it as is. And of course, this functor doesn't do any change when we're just performing an assignment. Another example is compilation of ternary expressions. If you have ternary expressions like this in your expression language, which is, I just use the C notation here, well, they represent implicit control flow jumps, and you can make them fairly explicit. Essentially, the functor is just going to inspect the expression being that appears either in an assignment or an assumption, break it up into assume the conditional, assume not the conditional, and then replace the expression with the correct branch. And so functors are a fairly nice tool because they're very modular. What we found is that if you apply the functor directly to the collecting semantics, and you can prove that that is sound, then you have a proof that the functor will be sound when applied to any sound domain. And conversely, if you prove that the functor applied to the collecting semantics is complete, it will also be complete when applied to any complete domain. And with that, we have a notion of soundness, of completeness of the functor object itself, and not just the functor applied to a function. And well, we have easy composition, which allows you to define very small functors which correspond to a tiny transformation, and then compose them to get a bigger compilation chain. And in practice, a lot of small transformations can easily be encoded in sound and complete functors. Like the two previous examples were both sound and complete functors. And finally, to tie in back to the previous section, so as I was saying, when you apply functors directly to the free algebra domain, what we'll notice is that the soundness of a functor implies a forward simulation, that is, that all traces of the initial program will also be traces of the target program, the program that's generated by the free algebra domain. And conversely, functor completeness implies a backward simulation, meaning the traces of the target are all traces of the source. And that's where we get a bit of a split between what we want between analysis and secure compilation. When you're performing analysis, what you want is to have another approximation of all your possible traces, and so you're interested in soundness. And when you're performing secure compilation, what you want is the opposite. You want the program you generate to be one of the valid traces of the source program, and you're mostly interested in soundness, in completeness. And finally, we looked a bit closer at compilation to a SSA form. So SSA is a single static assignment. So if I write the same program I had here in SSA form, you might notice, so the essential property is that each variable is defined only once. You might notice I'm saying that and throwing a slide where each variable is defined twice. We have R4 defined on both edges here. But the idea is it's a bit of a trick of annotation. The idea is R4 is actually only defined at the node 4. It's just that its definition depends on where you're coming from. And so if you're coming from node 3 prime, R4 will be R1. And if you're coming from node 3, R4 will be R1 times A1. And that is what traditional SSI denotes by with phi functions. But we chose to move these to the incoming edges because it's a little clearer. And so while these graphs look very similar, they're quite fundamentally different because the first graph you can have assignment and conditional edges wherever. In the second graph, you only have assignment edges above join nodes, and all assignment edges must define the same variables. And so when you have constraints like this, it's always interesting to try and have them directly in your type, so you know they will always be guaranteed. So what we did is change the domain signature a bit. Instead of having an apply function that could apply two kinds of relations, we now only have an assume function that just deals with the conditionals. And we've moved the assignments to the joins, where instead of having just a set of states, we have a set of states combined with the variable definitions that appear when we come from that state. And so we can perform compilation to SSA with a functor. It's a bit different and more complex. I don't really have time to present it here, but the gist of it is it's a functor that takes an SSA domain as argument and returns a classical domain. This one modifies more than the apply function. It also has a different state where it keeps on one side a mapping from old program variables to their corresponding SSI expressions, and on the other side, it keeps the SSI underlying state. This functor is sound and complete, and very similarly to the previous functors, we also have forward and backward simulation theorems when we're applying between the source code and the code we get when applying this functor to an SSA-free algebra. And so why are we compiling to SSA? Well, as I mentioned at the start of the talk, the idea that SSA appeared in compilation because it's popular, it's very easy to analyze. And essentially here we're going to use the property of immutability, so we can store numerical information not only about variables, but also the value of expressions, and we won't have to update them when expressions changes because all values are immutable. So for example, when we're trying to analyze bytecode like this, where we have some very elementary expressions and a lot of temporary variables, we can see that at the end we're assuming a conditional, which is an AND of two flags, which are essentially conditionals on the numerical value of y. Well, first of all, when we pass it through the lift SSA functor, that functor is going to inline all these and realize there is only one pertinent variable, which is the initial value of x0, and all of the variables can be expressed in terms of x0. And then the second step is using the numeric domain, which stores values not only about variables, but also some expressions, so we do not lose information we have about y, simply because it cannot be represented only about x. You can also store variables about these sub-expressions. And so what we found is that with this tool, compiling to SSA and then doing this numerical analysis, we could analyze bytecode with essentially the same precision as source code, which means that our analysis, while being completely non-relational, isn't affected by the fact that I can take an expression, breaking it up into small chunks with lots of temporary variables, and then perform them one at a time. So it's successfully able to recover context that is often lost in compilation. And so in conclusion, our contributions are a method to generate imperative and SSA programs directly as an abstract interpretation results, a method to implement and prove compilation passes using the functors I've presented, and then a non-relational domain that is more precise than what you would do directly because it benefits from the prior compilation to SSA. So all this work was implemented as part of an OCaml library, which is a codec library, which we recently were able to open source. And if I talk briefly about the limits of our approach, you can use most of abstract interpretation with it, but we are still performing a mainly forward analysis. So you could combine it with lots of different forward analysis, but you'd have you'd have much more trouble performing backwards analysis like liveness with this framework. With that, I can thank you all for your attention, and I'm glad you take any questions.
Great, thank you very much. If we have any questions, we have time for a couple of quick questions if anyone would like to move to the mic. I'm not seeing any question movement. Oh, we've got one over here, great.
Hi. Thanks for presenting the work. It's really interesting. I just have one question. Have you compared any performance of your analysis with existing analysis and seeing if they are algorithmically slower?
We've implemented it obviously, and the two questions we had when the implementation were, can we quantify this precision improvement, and what overhead does it cost? And so we noticed that both answers are rather correct. We get a 5 to 10% increase in numerical precision across various metrics we used. And for performance, we do get a constant overhead, which varies between 2 and 20, factor of 2 and 20, when compared to our implementation of just using the numeric domain. So we haven't compared it to other analyzers yet.
Thanks.
While our next speaker is setting up, we have time for one more question if anyone's got one. Or I can ask one, just a very annoying big question. Is it at all useful or interesting to try and retrofit this into an existing big compiler, or is it just a case of it's a whole different way of doing compilers?
Well, we're coming from the analysis world, and we're mostly worked on using the compilation to perform the analysis. So I don't know how much the compiler community will find this interesting and useful, but maybe.
Okay, that's fine. Okay, let's thank our speaker again. And our last speaker this session is Jamin from KIAST. What's the right way to pronounce that? KIAST. Okay, I'll just say that in future. And he will be talking about C to Rust transformation and don't write but return. Take it away, Jamin.
All right, can you hear me well? Good. Yeah, let's get started. All right, I'm Jamin from KIAST, and today I'll present our paper, Don't Write But Return, Replacing Our Parameters with Algebraic Data Types in C to Rust Translation. So the goal of this work is to automatically translate C code to Rust, and especially in this work we focus on our parameters in C and algebraic data types in Rust. So in this presentation, I'll explain how our parameters are used in C and how algebraic data types of Rust can replace them. And I'll show our approach to replace those during the translation. And this is joint work with my advisor, Seokyung Ryu. So Rust is a recently developed system programming language that tries to replace C in system programming. Its ownership type system can detect memory bugs at compile time through type checking. And this makes translating C code to Rust a promising way to enhance the reliability of legacy system software. By translating the code and type checking it, developers can detect previously unknown bugs and even prevent introduction of new bugs in advance. And noticing this potential, the system programming community has already started the transition from C to Rust. Notably, Linux has already added support for Rust in kernel development with its recent release. However, manually translating a code is hard to be correct. It's very time-consuming and error-prone. So it's desirable to have an automatic translation, and such automatic translators should meet the high expectation of developers to be used in practice. And it means that they should be able to replace some code patterns in C with proper language features in Rust. So, and one such an important language feature in Rust is algebraic data types, or ADTs. And in this work, we focus on two specific kinds of ADTs, namely options and tuples. And they are useful, especially useful, for when being used as the return types of functions. Options are useful for representing partial functions or functions that may fail on some input. Here, div divides n by d and returns the quotient. And this is a partial function because it fails when d equals 0. So its return type is option, and it returns none to signify failure when d equals 0, and returns sum of the quotient otherwise. And tuples are useful for representing functions that return multiple values. Here, this div returns both quotient and remainder, and for this, it constructs a tuple. Unfortunately, C provides neither options nor tuples. So programmers usually use a code pattern called out parameters. an output parameter is a parameter for producing output, but not for taking input. So here, in this example, div has an output parameter named q. And its return value is not for producing output. It's rather for signifying whether the computation has succeeded or not. So here, the return value of 1 means failure, and 0 means success. And the function writes to q only when the computation has succeeded. And in this second example, div has an output parameter named r, and it produces the remainder through r. And it directly returns the quotient as a return value. So as you can see, output parameters are quite useful in C, but they are generally discouraged in other languages. First, they can make code harder to understand because parameters are usually for taking input but not for producing output. In addition, output parameters are error-prone when they are used for partial functions. The return values of partial functions indicate whether the computation has succeeded. It means that the caller should check the return value to decide whether to access the value of the output parameter or not. And if the developer missed the checking by mistake, then the program can read a wrong value, which can lead to a bug. So it's desirable to replace these output parameters with proper ADTs during the translation. However, C to Rust, which is the most widely used translator from C to Rust, performs only syntactic translation. This is the translation of the previous examples using C to Rust. And you can see that the output parameters remain the same, and the return types also remain the same. In this work, we present techniques to translate C code to Rust while replacing our parameters with proper ADTs. We first translate C code using C to Rust to obtain Rust code still using our parameters. And then we statically analyze this Rust code to identify our parameters in the code. And finally, transform this Rust code using the analysis results to replace our parameters with ADTs. And in this approach, the most important goal is to identify our parameters without false positives. Here, a false positive means to classify a non-output parameter as an output parameter. It's harmful because it may change the semantics of the program after the transformation. To identify output parameters, we employ flow-sensitive data flow analysis. And we introduced the notion of abstract read and write sets to track the set of parameters read or written by functions. Here, X denotes the set of every pointer type parameter, and an abstract read set is a set of parameters. Here, the order relation is the usual subset relation. And if X belongs to the read set at certain program points, then it means that X may be read before being written while reaching that program point. In this way, we can over-approximate the set of read pointers. And on the other hand, an abstract write set is a set of also a set of parameters, but the order relation is reversed. So if X belongs to the write set, then it means X must be written before being read until reaching that program point. So in this way, we under-approximate the set of written parameters, and we can avoid false positives. So let's see how abstract read and write sets are updated during the analysis with some examples. Here, foo has two pointer type parameters, p and q, and both abstract read and write sets are empty initially. When the function reads from p, then we add p to the read set, and when function writes to q, then we simply add q to the write set. And in this second example, the function first reads from P. So we add P to the read set. And then function writes to P. But because P already belongs to the read set, we do not add P to the write set. In this way, we can ensure that this condition, if P belongs to the write set, then P must be written before being read to hold. And we want this property because we do not want to classify P as an up parameter. Here, the function uses the original value pointed by P. So if we remove this parameter during the transformation, then there is no way for the function to obtain this value. So we do not want to classify P as an up parameter, and so we do not P to the write set. In addition, we introduced the notion of write set sensitivity to distinguish different write sets during the analysis. It's useful when analyzing partial functions. Here, initially the write set and the abstract memory are both empty, and the function writes to x. So we update the memory accordingly, and the true branch of the if statement, the function updates x and writes to p. So we add p to the write set. And when the control flow merges, instead of joining these two different write sets, we simply keep both different write sets. So in this way, we can track the relationship between the value of local variables and write sets. So here we can conclude that the write set is empty when x equals 1, and p belongs to the write set when x equals 0. And finally, when the analysis is done, we can identify up parameters by inspecting the abstract state at the return point of each function. So we classify up parameters into two categories, must up parameters and may up parameters. So first, a must up parameter is contained in every abstract write set. So here, p is a must up parameter, and it means that the function always writes to that parameter. So we have to replace such a parameter with a tuple type. On the other hand, may up parameter is contained in only some of the abstract write sets. So here, p is a may up parameter, and it means that the function sometimes writes to the parameter and sometimes does not. So we have to return such parameters with an option type. And in addition, in the case of may up parameter, we can figure out which return value indicates failure and which indicates success. Here, since the write set is empty, when return value equals 1, we can conclude that the return value of 1 means failure and 0 means success. Now I'll show how we can transform code containing up parameters. Here, p is a must up parameter. So we remove the parameter and change the return type to a tuple. And we define a new local variable named pv, which means the value of p, and redefine this p as a pointer to pv. In this way, we can make the remainder of the function to work properly without any change. And finally, we change the return statement to return both the original return value and pv. At call site, we remove the argument and destruct the return value to obtain both produced value. We also update the pointer value accordingly. And the transformation of a may up parameter is similar but a bit more complex. Here, p is a may up parameter, and so we remove the parameter and change the return type to an option type. As before, we define pv and p, and we additionally define pw, which tracks whether the function has written to p or not. So it's initially false, and we change its value to true when the function writes to p. And when returning, the function checks the value of pw and returns sum only when pw equals true. And at call site, the original caller checks the return value to decide whether to access the value of our parameter. And we change such code to pattern matching. And for this purpose, we need to know which return value means success. Here, the analysis can find that 0 means success. So here, we can conclude that the true branch is the success case and the false branch is the failure case. So we map this true branch to the sum case and the false branch to the non-case of pattern matching. We evaluated our approach with 55 real-world C programs consisting of 35 GNU packages and 20 benchmark programs used by the previous work on C to Rust translation. We first evaluated the scalability of our approach, and we found that we can analyze and transform 90 kilolines of Rust code within about 200 seconds. And we also evaluated the usefulness in the sense that our approach is considered useful if it can identify many alpha parameters in real-world code. So we could identify about 30 alpha parameters per program on average. Finally, we evaluated the correctness of our approach using the test suite of each program. And among 26 programs that have test suites, 25 still passed all the tests even after the transformation. And the one failure case was due to a false positive related to an imprecision during the analysis while handling global variables. And we believe we can easily enhance the analysis to resolve this false positive. To conclude, in this work, we propose techniques to replace alpha parameters with ADTs during C to Rust translation. To achieve this, we propose a static analysis that can identify alpha parameters in the code. Thank you for listening, and I'll be happy to take any questions.
Great. Any questions? Please head to the mic.
The example where you choose an option type seems like a clear choice, but as soon as you go to some of the may return cases, how do you select, or do you generate a fresh type every time? Do you select the result type? Rust, for example, doesn't have a generic either type like Haskell, and result sort of implies an error just from the name. So I was curious what types you pick or generate in the other more complicated cases.
Yeah, thank you for the question. So in this presentation, to simplify the things, I used option type as an example. But in fact, in our real implementation, we are using result type always. That's because in this example, in the presentation, one was the only value for the error, the failure case. But in practice, there can be multiple error values or error code, and the caller may need that information to classify the kind of error. So to keep that information, we are using result type in our implementation. So the result of T, E, and T is the type of the value, and E is always the integer type because we are always returning the error code in the case of failure. So in our implementation, we are using the result type.
Okay, that makes sense, but you never generate algebraic data types with 3 constructors?
No, we are not doing this. So in this work, we are not dealing with, in general, ADTs, but we are focusing on only tuples and result or options. Yeah. Thank you for the question.
Very interesting project. So I have a question about, can you generalize your method to other language? There's a lot of language, both have the mutable variables of reference plus the ADT, right? So if some programmer writing a program using your input parameter simply because it can use reference, but it's supposed to return the ADT, something like this, can you generalize your method to this kind of language, or is it very specific for Rust?
Sorry, so what the original code
for example,
like?
there's like a Scala or OCaml, both have a reference or mutable variables and ADT, right? Some programmer maybe write a program use input parameters because simply you can support it. But of course,
you mean output parameter or input parameter?
Output parameters.
Yeah, I see.
It's simply supported, but is it supposed to actually return the result?
I see. So I think the approach itself is language agnostic. So I believe we can apply to other languages if that kind of code patterns are prevalent.
Okay.
Thanks for the interesting work and the great talk. I just had one question. Your whole motivation for the optional types was transforming them was that you can detect bugs where the user is not checking the return. But that still stays as it is. Like, are you pattern matching and inserting more error checking at the call site for the optional types?
Yes, when the option type is returned, we insert pattern matching to, get.
If it's originally not checked, that's what I mean.
Sorry?
If the original C code didn't check it, that was the motivation
Yes,
for your
I understand. So in Rust, there is no way to obtain the value without checking. So even if the original C code does not check anything, we are inserting the pattern matching. So it can be a bit inefficient compared to the original code, but so in our paper, there's a performance comparison, and we didn't observe a meaningful performance change after the transformation. So we believe that additional check would not be a big problem. Thank you for the question.
I wanted to ask a couple questions about your evaluation. Sorry. You've lost your lavalier. So on your evaluation, you gave us a data point of 90,000 lines of code in 200 and something seconds. I was wondering what the sort of scaling result was there. What is the time complexity of checking 40,000 lines or 180,000 lines?
Yeah, thank you for the question. So I have some graphs. So this is the size of code and the y-axis time. So I think it's a bit hard to find a clear relationship between the size of code and the time, because I omitted the fact from the presentation, but our analysis is a modular analysis. So we analyze each function independently, and because of that, if a small program has contains a very complex function, then it can take a lot because of analyzing the single function. So I think it's hard to say a simple complexity. So
that makes sense. So if I can follow up just quickly, how does your analysis scale with length of function or complexity of function? Is it exponential in the length of the function? Is it quadratic in the number of conditionals? Like what's
I haven't thought about the exact complexity, so sorry, but I couldn't answer exactly.
Hello, great talk, thank you. I wanted to know if there were next steps for making the final result a little nicer, because it feels a little crafty to like introduce this mutable pointer that then we're editing and then we're dereferencing. So like, of course, like it's a great result, but are there next steps planned for making that smoother, or is it way too like case by case specific?
Sure. Thank you for the really good question. And obviously the result of the transformation does not look that good. So, so in our paper, there is mentioned a bit of simplification strategy to remove some of those local variables, but we haven't implemented yet, and we are trying to implement those simplification strategies as future work. Thank you.
I had one more super quick question. What do you do if there's no else branch in the before? Do you just
then the don't branch will do not anything. Just empty branch here.
Oh, okay. Thank you.
Thanks.
Great. Let's thank Jamin again, and that's the end of this session.
and effects. Our first presenter today will be Taro, who will tell us something about gradual typing.
Okay, thanks for introduction. Hello everyone, I'm Taro Sekiyama. In this talk, I'm going to present the space-efficient implementations of a polymorphic gradual typing is possible if the polymorphism is restricted to be mostly parametric. Okay, so first, let me introduce what is a gradual typing briefly. Gradual typing is a type methodologies to enable the migrations between static and dynamic typing. And to do so, gradual typing introduces a special type, star, which is called the dynamic type. So the specialties in dynamic type is that the type check for the dynamic type is skipped at compile time, but instead it is deferred to the runtime. So okay, so let's see one example here. Here the successor function takes a value of a star, but it is converted to the integers, and then the successor of it is returned as the value of star here. And as I said, the static type checking for star is skipped. So both of our two function applications in below were typed. But such a type checking is deferred to runtime, which means that the Boolean value in the second function applications, it is checked that the Boolean values can be used as integers at runtime. But of course, it's impossible, so runtime error happens if such a type mismatch is found. Okay, and if the types of successor functions is turned to be more static, like int to int, then the type checking is shifted from dynamic checking to the static checking. So then we can find the second application is ill-typed. Okay, and this is a very brief overview of gradual typing, and there are many theoretical extensions of gradual typing. And in this talk, we focus on the extensions of parametric polymorphism. Okay, and the parametric polymorphic gradual typing is an extension of a gradual typing with a parametric polymorphism, and it supports universal types as usual polymorphic languages. But the distinctive point of polymorphic gradual typing is that it enforces parametricity at runtime. So parametricity is a crucial property of polymorphic languages. It ensures polymorphic values behave uniformly, independent of how polymorphic values are instantiated. And in the polymorphic gradual typing, the parametricity is checked at runtime. So it means that if programs try to break the type abstractions given by polymorphism, then some runtime errors happens. Okay, let's see one example. So here, ID star is just identity functions, and it is converted to the polymorphic identity functions through star dynamic type. So then ID star can behave independently of arguments. So it can be used as a polymorphic identity function. There's no problem. But if some successor, for example, successor functions is used as a polymorphic identity functions, it is possible by using dynamic type. Then the successor functions, the behavior of a successor function depends on the argument. So what argument is given here? So then the runtime enforcement of parametricity ensures that, okay, this function accesses concrete values of the argument, then runtime error happens. So then it can prevent the argument-dependent behavior. And of course, similarly, if the functions tries to dynamic analysis on type argument, then runtime error happens. So in this case, variable x has an abstract type big X, and then x is converted to the integers through the dynamic type. But such conversions breaks the type abstraction given by the polymorphism. So all of the function applications triggers runtime error, also in this case. Okay, and our long-term goal is to, so many theoretical aspects of polymorphic gradual typing has been studied so far, but our long-term goal is to obtain the efficient implementations of polymorphic gradual typing. But to do so, there are many open questions. So in this work, we focus on one question, whether space-efficient implementations of polymorphic gradual typing is possible or not. But unfortunately, in general, polymorphic gradual, parametrically polymorphic gradual typing cannot be implemented space efficiently. It is a known fact. But our discovery is that this is not the end of the story. So in this work, we show that it's possible to implement the polymorphic gradual typing space efficiently if polymorphism is mostly parametric, not a free parametric. So here, most parametric means that parametricity is dynamically enforced only if polymorphic values are instantiated with non-star types. Okay, so let's see one example to find the difference. So here, this is an example that converts the successor function to the polymorphic identity functions. So as I said, in a freely parametric semantics, both of the function applications lead to the runtime errors. But in a mostly parametric semantics, only the first function application raises the error. Because in the second applications here, the type argument is star. And in mostly parametric semantics, in this case, parametricity is not enforced. Okay, so in this case, the argument is just a pass to the successor functions and return the value returned by the successor function as it is. Okay, so then next, so this is an overview of our work. So next, I will talk about why this restriction on polymorphism can lead to the space-efficient implementations. So to explain it, first I need to explain the quotient calculus, because space efficiency is properties of intermediate language in gradual typing. And quotient calculus is one of the intermediate languages, and there runtime type conversions appear explicitly as quotients. Okay, so for example, let's consider one example here. This is a program in the surface language, and here number 42 is converted from into line, and then x has a dynamic type, but x is used as integers, so it's also converted from the line to int here. Okay. And this programs is represented in quotient calculus like this. So here are two quotients. So one thing comes from the conversion from the into star. And this quotient we call the injection quotient here. And the second quotient is into question. It comes from the conversion from star to static type. This program behaves like this one. So first, this projection function, injection quotient just attach the type tag to the value. So then 42 into bang is just a value with type tag int. And then x is replaced by the quotient injected value. But here into question checks the tag in the projection function the tag in the into questions is the same as the tag attached to the argument value here. So in this case, the two quotients have the same type tag, so the check successful. But if the integers, 42 number is replaced by the Boolean value, then the type mismatch happens, so then it leads to the runtime errors. Okay. And so this is a simple behavior of a quotient calculus. But we extended this quotient calculus to a parametric polymorphism. So to do so, first we introduced the notion of type names, which has been introduced by the previous work on polymorphic gradual typing. Yeah, and type names. Okay, so type names are generated to evaluate type applications. And this is an evaluation rule in our calculus for type applications here. And to evaluate this type application, first, a fresh type name alpha is generated. And then bound type variable x is replaced by alpha. The intuitions to understand this rule is that one of the intuitions is that type names can be considered as fresh base types. And type application generates fresh base types alpha. And we also introduced 4 kinds of new quotients to allow the interaction with star. The first two is for injection and projection for type variables, and the second two are projection and injection and projection for type names. But the notable point here is that the types over a quotient for type names are a bit non-standard. So here, type A corresponds to the type argument, type argument of the type application that generates type name alpha. Okay, so in this case, alpha, the type of A corresponds to this type argument here. Okay, and these 4 type names and quotients can enforce the parametricity at runtime. Let's see one example here. So this is an example that does a dynamic type analysis within the function body. So then this program is represented like this one in quotient calculus. So here x bang and so on is inserted. First, okay, so then let's evaluate these function applications. First, type applications is evaluated. So a new fresh type name alpha is generated here, and x is replaced by alpha. And but here x prime is replaced by 42 alpha bang. So then into question checks the 2 type tags are same, but alpha and int are different. So here random error happens. So this is why we can consider type names as a fresh base types. Okay, and okay, so next let's consider space efficiency. So very briefly speaking, space efficiency means that the space consumed by quotients at runtime is statically predictable. A bit more precisely, it means that if a consecutively applied quotient appears at runtime, then such a quotient can be compressed into a quotient whose size is bounded statically. Okay? So then, by keeping in mind this notion of space efficiency, we can show that the impossibility of space-efficient implementations by using the 3 facts. The first fact is that we can provide a program that generates quotient sequences that consist of injection quotients for n different type names. And the second fact is that the quotient sequence cannot be compressed into simpler quotients. And the third fact is that the size of this quotient sequence is not less than n. So using these facts, we can find we can find for any n, the program may generate can be evaluated to program state where the space over quotients may be larger than n. So then space efficiency doesn't hold in the freely parametric polymorphic gradual typing. But from these counterexamples to space efficiency, we can have key observations. So the first one is that the problematic quotient sequence is well typed only when for every type name alpha, the injection coercion has this type, start to stir. And the second observation is that such a type name alpha I is generated by type applications with star as a type argument. By using, okay, so then we can say that the impossibilities is due to the type name generation at type application of this home here. Then conversely, we can show that space efficiency is possible if the type applications with star as a type argument generates no type name. This is our observations. Okay, let me summarize what we achieved formally. So we've provided two coercion calculus, so lambda C and lambda S. And both calculus employs mostly parametric semantics. And we show that parametricity holds on the first coercion calculus, lambda C. And lambda S is equipped with space-efficient semantics. And actually, under it, we show that it actually satisfies the space efficiency. But to do so, we also introduced new coercions, which is necessary to represent type analysis on whether type argument is dynamic or not. But I skipped the details in this talk. Okay, this is all of my talk. Thanks for listening.
We have time for a few questions.
Hi, my name is Jeremy Seek. My question is about the restriction from sort of a practical standpoint, thinking about like when we would be using parametricity, maybe to prove free theorems or stuff like that. Do you see the restriction as, or do you foresee it as something that would get in the way of people using free theorems, or is it like no big deal? I mean, I think I know the answer, but I'm curious, like your thoughts on that.
Yeah, thanks. Yes, it's a very important questions, especially for applications. Yeah. So I'm not so familiar with the compiler techniques, but I hear that free theorems parametricity can provide many free theorems, and free theorems are very useful in the compiler optimization. It is one thing. And the other thing is that parametricity can be related to the security verification, like a non-interference. So if we apply such a technique in a gradually typed setting, then I think parametricity is totally important. But I'm not sure this mostly parametric polymorphism is still useful for such a context. So we need to explore.
Sure. I mean, I think, yeah, you're being humble. I think I think in a lot of applications of parametricity, you're going to be wanting to use specific types to instantiate. So I envision that this restriction is not all that hard of a restriction. That in many cases it'll be just fine. So.
Yeah, thanks.
Okay, let's thank our speaker. Okay, so next up is Matthew, who will tell us about associated effects.
Thank you. I'll start with an introduction to effects in general. So an effect system is something that will track the actions that a program can take. So this can be something like resource use, memory management, exceptions in Java, for example, as well as algebraic effects, which is a control flow mechanism, if you're familiar with that. When you have an effect system, you'll typically see the effects showing up in type signatures for functions. So here in the right line function, you see on the right, we have the console effect annotated on the right of the function. And we can also have multiple effects. So a read file function might have an IO effect and the possibility of throwing a file not found exception. We can, of course, have no effect if we're dealing with a pure function, like concatenating two strings. And we can also have effect polymorphism. So when you map over a list with some function, that function f will have some effect here, ef, and then executing that map function is going to have that same ef effect. Now what I'm interested in here in this talk is how do we integrate effect systems and type classes? And to show you why that's not hard, or why it is hard, I'll take you through a few examples. And the first example is with overloading arithmetic operators. So if you imagine that we can add floating point numbers, which is easy if you try, we might have a function like this specifically for floating point numbers. And then we can also have a separate function for adding integers together. But it's kind of annoying to have these two different functions for adding things when adding things is kind of the same everywhere. We want to be able to use just the plus sign for adding. And in a functional language, the typical way to overload an operator or a function is with the type class. So here we have an add type class, which lets us overload that plus operator. And then we can create an instance for each type that we want to add. So we have an instance for integers, and we have an instance for floating point numbers. And each of these delegates to that specific implementation that we had before. If you buy that, then you might also buy that we can divide floating point numbers. Here we have a special division operator for floating points. And it's not much of a stretch to say that we can also divide integers. But if you believe that, then you've been fooled, because we can't actually divide integers, at least not all the time. Integer division can lead to a division by zero error. But floating point division actually cannot if you're following IEEE RFC 700 something, which says that division by zero is not a number or it's infinity, depending on your arguments. So if we want to abstract over this like we did with the addition and define a division type class, we actually have a problem, because floating point division is total, but integer division is partial. So when we have this division by zero exception in dividing an integer, we need that in the effect signature. So what effect signature does division have? It can't be pure, because we need this division by zero, but it can't be division by zero because we need this, this purity for floating points. So more generally, the problem that we have is how do we make one type class abstract over both partial and total functions? So that was our first example. Another example is dealing with iteration over collections. In Flix, which is the programming language that I'm using here, a mutable data structure lives in a region. So here we have an immutable list, which is our standard cons list, as well as a mutable list, which has both an element type A and this R, which is the region where this mutable list lives. And that means that when we observe data in this list, we're going to have that region effect in the signature. So the pure head function for an immutable list has the pure effect. There's no effect. But the impure function for observing a mutable list has that R effect, the region of the mutable list. Now, if we want to manipulate this data, for example, by folding over it, well, folding over the immutable list is fine. We just have that a similar signature to what we had with map at the beginning, where we're polymorphic in the effect EF. But when we fold over a mutable list, we actually have this union of effects, because we're both observing the list and affecting or executing the effect of F. So again, we have a similar problem. If we want to generalize this folding operation, say with a type class foldable, then we end up with a problem, because we have these mismatched effects. One of them is EF, and one of them is EF plus R. So again, more generally, the problem that we have is how can we make one type class abstract over both mutable and immutable data? And the third example I have is dealing with data streams. We have this reader class, which will read bytes from a resource into an array. The resource, it has type T there. It's called RD. And the effect of this is R, the array that we're reading into, plus IO, because presumably we're doing some IO operation to read. And this is appropriate for something like reading from standard in, because that indeed is an I/O operation, and we're modifying the array as we read into it. But for something like a string reader, well, reading from a string isn't an I/O operation because the string is not any kind of I/O thing. It's just some mutable value, or the string reader is a mutable type. And so the effect of this is R plus R1, not R plus I/O. So once again, we have these incompatible effects. So problem 3 we have is how can we make one type class abstract over different element types, or different effects of effectful operations. So to summarize our problems, we want to be able to define type classes that abstract over the effect signatures of partial and total functions, mutable and immutable data, effectful operations, and there are several other problems that I won't show today. The solution that we propose to this is something that we call as an associated effect. And this is an effect that we associate with a type class, and we select it for each instance. And we'll go back to that first example to show you how it works. Here, again, we have this div class, but in addition to the div member function, we have this type AEF, and this is our associated effect. Then in the signature of div, on the right-hand side, you see in the effect position, we have AEF. Now, when we implement an instance of div, we're going to select what that associated effect is. In the case of integers, that's going to be division by 0, because as we established, integer division can lead to a division by 0 exception. In the case of floating points, we're going to define the associated effect as pure, because floating point division is total. We can do the same thing for foldable. Again, it's a similar solution. We will add this associated effect, and then the effect of fold left is going to be the union of EF, the function f's effect, and our associated effect. So when we fold over a immutable list, we define AEF as pure, and therefore our effect is just the effect of f. But when we fold over a mutable list, our effect is the region R, and so our overall effect of fold left is going to be EF plus R. And finally, the story is the same for that reader. Here we will define the effect as R plus AEF. Then the standard in reader will be R plus IO as we had before. But for the reader of string reader, we define AEF to be the region of our string reader. And so the read function has the effect R plus R1. So that's the theory. What about in practice? So we have a full implementation of this in the Flix programming language. And we've expanded the standard library, first with a refactoring and then an expansion with what we've unlocked with associated effects. So briefly about Flix, it's not a toy language. It's actually a proper language by some measure with a bunch of features, including standard things like algebraic data types and non-standard things like first-class data log constraints. And again, just as evidence of it's not being a toy, we have several thousand, 100,000 lines of code, a bunch of library functions, and a bunch of library lines of code. We made a lot of changes to support associated effects, but they were fairly simple changes with modified classes to add these associated effects to them, modifying the signatures to include those associated effects, and function signatures that use those type classes. Thanks to this refactoring, we were able to define instances for mutable data types. So for iterable, foldable, unordered, foldable, and toString, all of these classes were previously only defined for pure data types due to this inability to abstract over the effect. But now we can define them for all these 7 extra mutable data types, in total getting 28 additional instances in our library. We have a calculus for this, which I will not present at all. But it's based on this work, Associated Type Synonyms by Chakravarti and friends. And if you're interested, you can take a look at our work and their work. So in summary, I've presented associated effects, which are an integration of effects and type classes. They allow for abstractions over partial and total functions, as well as over mutable and immutable data, and abstractions over effectful operations. Our contributions include the idea of associative effects, as well as the type system and implementation, and the expansion of our standard library. For more information, you can check out flix.dev. And that's all. Thank you.
Okay, I think we have time for a lot of questions.
Did you try implementing something like this in Haskell, or simulating it in Haskell on top of, I don't know, associated types or some other features?
No, we did not attempt that. Indeed, this, of course, bears a lot of similarities to associated types, and Chakravarty's work is...
Do you have reason to believe it would not be doable there, or
I have no such reason to believe, no.
So it may well transfer
to
yes. Other type class systems. Okay, thanks.
Mm-hmm.
Hey, thanks for the great talk. I can imagine you might find yourself in a situation if you're writing a new trait, basically, that you're sort of defensively adding a associated effect because who knows what the implementer might require. Sure, it can default to pure or whatever.
Yeah.
And on a related note, I'm aware of a sort of nascent initiative in the Rust language that it's sort of targeting API compatibility. And I think you can basically think about it as they're adding associated effects to the instances, to the implementations, but they're not present on the trait. So the idea is that you can sort of like implement a trait in a context where you couldn't normally do it. So how are you approaching thinking about this in terms of like, API design and things like that?
Sure. So there are a couple things. So one is there are certain traits where you definitely do not want, or very likely do not want to have associated effects. And one example, for example, is equality. It's usually bad for equality to have an effect because if you're searching through a list, you don't want to have to execute a bunch of effects while looking for this this item in the list. So that's one thing. We are aware of some efforts in Rust. I think, for example, they have this trait that's async iterable and regular iterable, things like that. And it definitely seems like very much related to what we're doing here. I don't quite remember what the other part of the question was.
I mean, I guess the question was, equality is a good example of where you might not want one.
Yeah.
But that one's very straightforward. I guess, like, did you find yourself, for example, when you were adding, associated effects to the standard library, being like, well, I can't quite think of what the effect might be here, but it cost me basically nothing to add it, so I might as well just do it.
I think when we were dealing with the standard library, mostly we were dealing with mutable and immutable data types. And so there it was very straightforward. It's going to be the region where our mutable data type lives. But I can indeed see that kind of defensive thing could be an interesting problem.
Okay, thanks.
Hi, could you please underline what are the differences or different issues that you encounter with associate types compared to just associate types? Effects and types, because it seems like very similar thing. So what's the difference really?
Yeah, so indeed it is very similar. And it's effectively just the placement of where it is in the signature. And so our contribution here isn't that associated effects is like a whole new thing compared to associated types, but rather it's identifying it as kind of a very important thing to realize that you want to have when dealing with type classes and effects. So in terms of a difference, there's almost not one, but it's rather identifying this as an important feature.
Okay, thanks.
Hi there. So my question is, if the mechanisms that you have to prevent certain, let's say that you have a function and you don't want this function to have an I/O effect and you want to prevent that to have that effect, is that the same mechanism that the underlying language uses for associated effects? Or
so
if you want to enforce some effects to have some or not have some others, in a function.
So if you're just dealing with a function rather than a type class?
A type class, yeah.
Sorry, can you repeat the question?
So let's say that I have a type class, and then I have the inner type T, and then I have this function, and I just want it for certain types that do not have a certain effect. So is there any mechanism for preventing functions to have a certain effect with associated ones?
So are you saying that the type class itself needs to say that no instance can have this effect, or?
Yeah. I don't want it to have this effect, but I want the other
to allow
types.
any other effect?
Yep.
Yeah, so Flix actually has this idea of effect exclusion, which you can see in a previous paper by us, where you can explicitly say, I don't want it to have, for example, the throw effect or some specific other effect. And that is possible with these associated types.
And it works perfectly with associated effects, right? Okay,
yeah.
Very cool.
Can you flip back to one of the slides that declares an instance that has an associated effect?
Sure.
I have a syntactic question.
Okay.
I noticed that when you declare like the associated effect, it's parameterized by the same thing that the type class is parameterized by, but in all the examples, like it's just the same. Is there a case where the second thing would be different?
There is no such case. It has to be the same, and in fact, in a previous version of the slides, I did not include that in the syntax, and then I was told that was confusing. So, yeah, it's always going to be exactly the same.
Okay, makes sense.
I think that whoever made that suggestion was wrong.
Okay.
Can I ask a question? And
then
you can repeat it because
sure.
I can't go there. Why associated effects and not maybe parameterizing the effect within the type class? So if we're sticking to the same slide, why don't you do class reader T, comma E or something like that?
Yeah, so
repeat the question
sure.
so that it comes up.
Yeah, so the question is, why don't we use multi-parameter type classes, right? So there are a number of advantages and disadvantages. The main thing that we're concerned about here is that the effect is uniquely determined by the type. And so we don't want to have a situation where there could be overlap or anything like that. It's really a one-way kind of a function rather than a relation. And so in this case, associated effects is, or associated types or effects is the most appropriate thing in our opinion.
Okay, so let's thank Matthew. Okay, our next speaker is Benjamin Chung, who will tell us about Julia.
All right, thank you very much. I should start with a caveat. While I work for Julia Hub now, my views are my own and don't represent those of Julia Hub as a company. All right, so what I'll be talking about is decidable subtyping of existential types in the Julia language. To begin with, I'll show you a real bug report. So this user, who admittedly is a Julia developer and thus is slightly self-inflicted, tried to add a method definition. Note, a method definition. They didn't try to call it yet, and it caused the language to Stack Overflow. This is sort of bizarre, and what happens to you if you run into this is that Julia will just sort of die. Like, you'll get a completely nonsense stack trace. It'll be very unpleasant. And the reason why, to sort of spoil this a little bit, which you might have done for yourself if you read the title of the talk, is that Julia tried to do some subtyping, and it went very wrong. So what's going on here? Is this a bug in Julia's implementation, or is this something that's more fundamental and theoretical that's going on here? If we go and look at the implementation, it's kind of complicated. It's 5,000 lines of C code written by only a couple of people. There's absolutely no formal specification of it. There's some inference rules, but they're not strictly followed. And there have been hundreds of issues that have came up over time that have mostly been resolved, but they illustrate that there's bits of this that people keep running into. So to spoil this a little bit more, this is actually an undecidable problem. These issues that people are running into where Julia will start stack overflowing and infinite looping in strange places on them is actually a consequence of the fundamental undecidability of Julia as a subtype relation. The reason why this is particularly important in Julia is because undecidability is something that comes up at runtime. The challenge is that Julia is an untyped language and thus is resolving subtyping queries as a part of its dynamics. When you make a function call in Julia, it can be invoking subtyping. When you define a new method definition, like I showed earlier, subtyping. When you write to a mutable field, if Julia wasn't able to type in for it, more subtyping. And even when it's JIT compiling, Julia is doing subtyping. And if you run into one of these infinite loops, if you run into one of these degenerate cases, it can suddenly crash on you in confusing and unpredictable ways. And your dependencies can bring this in on you. It's just an unpleasant experience all around. So the key insight that I'm going to talk about in the rest of this presentation is how we can take the sort of larger undecidable language of types in Julia, identify a restricted type grammar of it that we can show as decidable, and then give a formal guarantee that you're always, or it would be better to say, and give a decision procedure for which we can show subtyping. The key question, let's see, right. So for the rest of this, to outline the rest of this talk, our type language, the type language that we describe is a little bit more restricted from the full family of Julia types. We miss out on a couple of features that aren't strictly necessary here, like distributivity of tuples and unions, nominal subtyping relations, and the diagonal rule. If you're interested in the details of these, please see our paper. In terms of the technical details, what we do is we present a declarative formalism of subtyping in Julia. We then extend this declarative formalism of subtyping in Julia, which has an explicit transitivity rule, to an invertible one that bakes in the transitivity into the subtyping relation. This was quite hard to show decidability properties. We did this because it was quite hard to show decidability properties about the declarative version because we constantly had to be reasoning about whether transitivity would apply in a given case. We then prove undecidability of this invertible version, and by the relation backwards, we're then able to show that the general subtyping in Julia is undecidable. Then we identify the stratification of Julia's type language that I mentioned earlier, restricting the grammar of types that is allowed to one that is decidable. We describe a stratified invertible subtyping for the subset of types. And then finally, we describe our algorithm for deciding subtyping in this restricted language. Okay, so to give a very quick overview of the language of types that we support in Julia, we capture the top type, the bottom type, type variables X. I'll talk a little bit more about this later. Tuple types, invariant constructors. So the broad takeaway here is that if we're doing subtyping of these, all of the types have to be equivalent to each other. Again, I'll talk about this more later. Union types, and this sort of nasty existential thing that I want to focus on in more detail. What's going on here when we write this type is that it corresponds to this generic union. What I'm saying here is that we have this type variable X that needs to be a subtype of the upper bound and a supertype of the lower bound. The denotation of this type then is the set of all types formed by substituting X for some valid instantiation of that, some sigma X here that satisfies the subtype relation. The challenge that this begets is that an algorithm for deciding subtyping in this setting needs to find some satisfying instantiation here. This is taken from our declarative calculus, and we have to come up with this sigma X from somewhere. This is challenging for a decision procedure for subtyping because sometimes it can be tricky. This is also where the undecidability comes from. The way that we show undecidability of subtyping in Julia is by reduction from system F sub p. What we do is we take a subtyping judgment in system F sub p, which is universally quantified, and then translate it through, and then provide a covariant translation to an existentially quantified version in our Julia subtyping relation. We're then able to show that the Julia subtyping relation holds if and only if the relation in system F sub p holds, and therefore, if we were to hypothetically have a decision procedure for subtyping in generic Julia types, we would therefore have a decision procedure for subtyping in system F sub p. We know by Pierce's work that system F sub p is undecidable, so therefore subtyping in Julia is undecidable, both for a restricted language and for the broader language of types in Julia. Now, the translation that we define for terms in system F sub p to Julia judgments does not actually use the entire language of types that I described earlier. The sets of types that uses are the bottom type variables, invariant constructors, and that nasty existential case. What's going on here is that we're relying very strongly on the impredicativity of existential quantification in Julia. What's essentially happening with this translation is that we're slipping in an existentially quantified, an existential type term into what this variable has to be instantiated with, and then it's sort of snowballing downhill from there. The problem that we run into then is that we can't just knock off impredicative existentials from Julia. They do actually appear in Julia code. As an example, where this starts to show up is that Julia has lots of sort of predicative-looking typed method declarations, like here with VCAT. This feels like this should only be instantiated in a predicative sense, in that we might have adjoints of int over vector of int. And we write this in our calculus in this form with a top-level universal quantifier. The problem is that Julia developers will frequently also use these types to describe heterogeneous data. To do this, they'll use a nested existential binding where we're saying that this is a vector of vectors of any type. So this vector could contain both a vector of int and a vector of string and a vector of char, etc. This nested existential binding, if we then check subtyping, can then flow up to that top level variable, requiring us that we instantiate that type variable with this existential, thus forming the basis for this undecidability. In this particular case, though, we observe that we can represent this particular use case with a different kind of more restricted existential type, use-site variance, akin to Java wildcards. This version with the wildcard represents the same set of types as the version with the unrestricted existential types that I showed above. Our key observation then is that we can combine these top-level existential bindings, like this X here, with use-site variance that's in nested locations to restrict impredicative existential types to a set that's still useful, which I'll talk about in a little bit, but we're able to show decidability for. This brings me to our core type stratification. The way that we stratify Julia types is into method signatures and value types. Method signatures consist of tuples, of top-level existential bindings, unions, and the bottom type. Critically, we do not allow these method signature types to recursively appear inside of the argument positions for the signature, as well as in the bounds for the existential quantification. Instead, these locations are inhabited by our value form, which consists of a more extensive grammar. But importantly, we restrict the value type instances, the invariant constructors and value type instances to only be quantified over using use-site variance. You're not allowed to have arbitrary existential variables appear in these invariant constructors. Then only these top-level signatures are introducing what we refer to as flexible variables, variables that we have to deal with in our ensuing constraint solving step. Once all of these flexible variables are then handled at the sort of top level, subtyping then becomes a lot simpler, avoiding the nasty constraints that led to non-termination. Notably, not all Julia types can be stratified. For example, here I have a vector of dictionaries that have the same key and value type. This can't be represented in this form because this requires that that the instantiations of the dictionary are coupled to one another. In our restricted form, these use site variances are unrelated to one another. The closest that you could get is a dictionary of keys that were subtype of something, but that's the best we can do here. I'll talk a little bit later about the practicality of this restriction. Now, coming back to the outline, we use the stratification to define a decision procedure for a stratified type language. Our procedure builds and resolves simpler constraints compared to what generalized Julia would do, giving us our decidability guarantee. I'll first walk through an example derivation from our algorithmic relation, then cover sort of a high-level overview of how the algorithm operates. Here, what I'm trying to do is check if a dict from strings to ints is an instance of the polymorphic type, describing dicts of any consistent key type to some heterogeneous instance of num value. So for example, this could also be a dict of strings and union of int and float. The type on the right here, written in the form that I described earlier, is equivalent to this existentially quantified version in base Julia types. What's happening here is that we're replacing this flexible variable v that we would have to deal with during constraint solving with this use site variance form. The way that our algorithm proceeds is by breaking down the existential on the right into something that we'll have to solve, and then checking subtyping of the two dict types. The value position is easy to check because of our simplification. All we have to do is sort of do the textbook check to make sure that the subtype relation holds in each direction, because this is an invariant position. So we need to show equivalence of the value of the element in value position. But the element in key position is a little bit trickier. The challenge here is that this k is a flexible variable. We need to figure out some constraints on what it can be instantiated with. And we do this by when we check to see if k is a subtype of string, generating the constraint that k is a subtype of string, obviously, and the opposite case as well. We then combine these constraints together. We then union them to produce a set of constraints that are necessary to be satisfied for the relation to hold. And then we check to make sure that they're sane and consistent using another judgment. The way that this judgment proceeds is just by ensuring that all of the lower bounds that we've discovered on the flexible variable are subtypes of the upper bounds that we've discovered. So in this instance, that string is a subtype of string, which trivially holds. The critical thing that our algorithm exploits is that these constraints that we built up over time, because of the structural restrictions that we've put on the types, are free from flexible variables. We'll never end up checking that k is a subtype of v or vice versa. As a result, this constraint resolution process won't produce additional constraints on flexible variables, thereby preventing us from having potential cyclic dependencies between the instantiations of flexible variables. To provide a more comprehensive overview of our algorithmic subtyping relation, and for more details, you'll need to check out our paper, we start with signature subtyping, so subtyping of method signatures, from which we proceed by unpacking existentials on the left-hand side, and then pulling the existential quantifications on the right-hand side off until we're left with some base value type tau. So the existentials on the right become flexible variables that we'll need to instantiate later. We then collect up all of the constraints that are begotten by the subtyping relation that we're checking on those flexible variables that we've discovered, and then pass that off to the constraint resolution mechanism I described on the previous slide. The constraint resolution mechanism then relies on value type subtyping, which cannot depend on producing constraints in order to resolve a judgment, ensuring that it terminates. To evaluate the practicality of this restriction that I've described, we evaluated it over a corpus of packages consisting of all publicly available Julia packages. This has 9,000 packages in it, comprising about 16.5 million lines of code. The way that we did this is we parsed all of these Julia files using the Julia parser. We extracted the type annotations and type declarations from this, identifying 2.2 million types. We processed these according to the type language that I described earlier, types that we could not parse consisted mostly of types that were built using metaprogramming, so our static analyzer wasn't able to figure out what those variables would be instantiated with. Of the types that were partially processed, those consisted of types that did not fully conform to our restricted language. So for example, ones that required the diagonal rule to resolve. And 2.25 million of these types were fully processed by our approach. Of the types that we analyzed, we identified 4 types in our corpus that did not satisfy the stratified restriction. So, in summary, what we did is we described a declarative subtyping relation for a large subset of Julia types. We then proved that this subtyping relation, and by extension Julia's own subtyping, is undecidable by reduction from system F sub p. We then identified a practical stratified subset of Julia's type language and defined a decision procedure for subtyping in this subset. Finally, we performed a corpus analysis over all publicly available Julia packages to show that our restriction is practical for almost all Julia programs. Okay, thank you very much.
Yeah, go ahead.
Hey there, nice to meet you. I'm Alessandro, and I work a lot with Julia, so I'm really interested in your work. I was already following Jan's works. And congratulations, because that's a huge amount of work. And my question is mostly related to how the Julia type inference is done, right? So it's done in C, it's a huge file, and it's really hard to read. And this work is really nice, and it gives some theory in order to improve that. So do you see any foreseeable plans in the future to actually rewrite, for example, that type inference using your algorithm? Do you have a fork of the Julia compiler?
So we don't have our own implementation of the subtyping algorithm. The other thing that I would say is that Julia's type inference algorithm is still a lot more complicated yet than subtyping. While you could use our algorithm to back type inference in Julia, it would be a lot of work to formally describe and prove correct that Julia's current type inference is actually safe. I think that a project that would be really interesting for the Julia community going forward would be rewriting Julia's type inferencer in Julia, and I think that that's something that's becoming more possible as time goes on. But currently, that's not something that, as far as I'm aware, is actively being worked on.
Yeah, there's not much programming language, practical work done. And my second question, if you want to catch up later, maybe, I'd be curious about what these 4 types were that you weren't able to resolve.
Absolutely. We list all of them in the paper as well.
Oh, yeah, okay. Thank you.
Okay. Any other questions?
Okay, let's thank Ben again.
Now it is on? Yeah.
Okay, great. Our next speaker is Ariel Callison, who will tell us about numerical fuzz.
Thank you. So this talk is about a functional programming language called numerical fuzz, featuring a type system for rounding error analysis that's particularly useful for understanding the behavior of programs that evaluate floating point expressions. So for this PLDI audience, let me describe the purpose of a rounding error analysis, which is to derive an a priori bound on the effects of floating point rounding errors on an algorithm. But the problem is that sound tools that automatically perform rounding error analyses tend to give pessimistic bounds and scale poorly. By pessimistic bounds, I mean that these tools might often return to us that the error is upper bounded by infinity, which is generally not a useful result. And by scaling poorly, I mean that these tools usually only work on benchmarks with fewer than 40 floating point operations. So we can see an example of this problem in practice by considering polynomial evaluation. So in polynomial evaluation, we're given a value for the variables of the polynomial, as well as all the values for the coefficients, and we're asked to evaluate the polynomial at those values. Pretty simple, right? And you might recall from earlier on that in your education at some point, maybe computer science, that a common algorithm for polynomial evaluation is Horner's scheme. So here we rewrite the polynomial using nested multiplications and additions in order to reduce the number of operations. So we can find an implementation of Horner's scheme in the NumPy polynomial library as the polyval function. And so here is the snippet of the documentation for that polyval function from that library. And we can see that in addition to saying that it evaluates a polynomial at specific values using Horner's scheme, we also have the following warning from this documentation: that for polynomials of high degree, the values may be inaccurate due to rounding errors, and that we should use this function carefully. So that may or may not be a very helpful snippet of documentation in the case that you want to use this function, right? And it probably brings up a few questions, but the one that's most important for this talk is actually how inaccurate should we expect this result to be? Okay, so the issue at hand here is that Horner's scheme is an algorithm that's assumed to operate on real numbers, and all of our operations are assumed to be infinitely precise. But polyval is a floating point program operating on floating point numbers, and all of the operations are finitely precise floating point operations. They are not infinitely precise. So the semantics of a floating point operation is that it should behave as if it's computed in infinite precision and then rounded to fit in a format. That's what this little diagram shows. And every time the rounding for the results of a floating point operation occurs, some error is incurred. Now, if we're working, for example, in binary 64 or double precision, we know an upper bound on that error. So it should be something like 2 to the minus 53, depending on the rounding mode and some other details. But this only tells us the error associated with a single floating point operation, right? And our polyval function is the composition of many such operations. So we still need to answer this question of how inaccurate should we expect the result to be. Now, if I were to turn to the literature to try and answer this question, I would immediately run into our original problem statement, that existing tools tend to generate pessimistic relative error bounds. Okay? So in this table, I have the relative error bounds listed from two tools from the literature, FP Taylor due to Soloviev in 2018, and GAPA due to Melchion in 2006. Okay, and we're looking here at benchmarks of Horner's scheme applied to polynomials of increasingly high degree. So Horner 2 is Horner's scheme applied to a second order polynomial. There are only 4 floating point operations. That's what that second column shows there. All right. And what we want is for these relative error bounds produced by these tools to match this target relative error bound. That's like the theoretical worst case relative error bound. It's known in the literature if you open up a numerical analysis textbook. But you can see, and maybe it's been a while since you've seen scientific notation, but the best performing tool there is 5 orders of magnitude off. 5 more orders of magnitude greater than our target relative error bound. So that's not going to provide you with a useful error bound in practice. Okay, so our contribution to solving this problem is numerical fuzz. It's a functional programming language featuring a linear type system for rounding error analysis, and it's sound, it's useful, and it's fast. So, how does it work? Well, it combines 2 key ingredients: a local rounding error analysis, which tells us the rounding error produced locally by a function, with a sensitivity analysis, which tells us how functions amplify errors from inputs. Sorry. Okay. So, to understand how a local rounding error analysis works, let's consider a function f here that takes a numeric value as an input and returns a numeric value. We can conceive of f as having 2 different semantics, and that's what this diagram here is supposed to show, so keep that diagram in mind. An ideal semantics, where all of the operations in the body of our function are assumed to be infinitely precise, and a floating point semantics, where all of the operations in the body of the function are assumed to behave like a floating point operation, so that is they're computed in infinite precision and then rounded to a destination format. The local error is then the difference between the results of applying f under its floating point and ideal semantics to the same value. So our key idea in numerical fuzz was that local rounding error behaves like a computational effect. So if we think of effects as what programs produce during evaluation other than values, then floating point programs produce values and rounding error. So in our work on numerical fuzz, we used a graded monad to track local rounding error. And the semantics of the graded monad that we used was a novel contribution of our work, but I'm going to leave the details of that to our paper, and instead introduce here an intuition behind the syntax. Okay, so if we have a function that returns a value of the following graded monadic type. Then it produces numeric outputs, and at most Q rounding error, where Q is an extended positive real number. And you can see now we've replaced the local error here in our little diagram by this value Q. That's the grade on the monadic type. But now we should ask ourselves what happens under composition. Okay, if you are someone who has developed rounding error analysis tools before, you'll say yes. What happens to rounding errors under function composition? This has been a challenging problem. So if I have our function f that produces at most Q local rounding errors indicated by its type and is shown in the diagram there, and I have a function g that produces at most R local rounding error as indicated by its type and is shown in our diagram here, then what is the total rounding error of the composition of G with F? Okay, we do not yet have enough information to answer that question. We have a missing piece in our diagram. And that missing piece is how does G, under its ideal semantics, propagate the local error produced by the function F? So this is where we come to the second key ingredient of our work, which is a sensitivity analysis, which tells us how functions amplify errors from inputs. Now the key idea with a sensitivity analysis is C sensitivity. And a C-sensitive function is one that amplifies errors in its inputs by at most a constant factor of C. So for example, again here in our diagram, if we know that our function G under its ideal semantics is, for example, a K-sensitive function, then we will know by how much it amplifies the errors produced locally by the function F. Now the idea of C-sensitivity was first integrated into a type system by Reed and Pierce in 2010. So that is not the novel contribution part of our work. And it was integrated into a type system, and it first appeared in this fuzz programming language. So now maybe you see where we get our numerical fuzz name for our language. And in that work, they used a graded comonad to track C sensitivity. And the application domain was differential privacy, so totally different area. And the intuition there is that functions that have the following graded comonadic type as an argument, values with this type, amplify errors by at most a factor of k, where k is the value there on the grade. And again, k here can be any positive real constant or infinity. All right, so now in numerical fuzz, we answer this question of what happens under composition for rounding errors using the combination of the local error analysis and a sensitivity analysis. So we know now if our function f produces at most q local rounding error and our function g is k-sensitive in its arguments and produces at most r local rounding error, then the composition of g and f will be a k-sensitive function that produces at most r plus k times q rounding error. And this is actually guaranteed as a consequence of our error soundness theorem, which is our main soundness theorem in our paper. And it says that well-typed programs of graded monadic type satisfy the error bound that the type system assigns it. More formally, if E is a well-typed program with a graded monadic type where the grade value is U, then we know that E will step under an ideal semantics to some value V1 and under a floating point semantics to some value V2, and that the distance between these two values is upper bounded by the grade on the type. So that is what our soundness guarantee looks like. And now when I introduced the contribution of our work, I made 3 claims: that it was sound, useful, and fast. We've seen evidence that it's sound, but what about being useful and fast? So let's talk about our evaluation. We have a prototype implementation of a type checker for our language following a sensitivity inference algorithm due to Azevedo de Amorim and co-authors from 2014. And so here is a nice little program written in our language. It takes 2 arguments, x, and it's too sensitive in its argument x, and it takes an argument y. We have a floating point addition, a floating point division, and so what it's actually doing is dividing x by the sum of x plus y. Okay, and then our type checker, we run it on this program, and it tells us, it infers an error bound for this program. We have 2 floating point operations, and so it tells us that it's the error bound on this program is something like 4.4 times 10 to the minus 16. So that's nice. Okay, let's come back to polynomial evaluation, which we started off with. Numerical fuzz generates optimal with respect to the worst case theoretical error bounds results. All right, so again here we're looking at Horner's scheme applied to polynomials of increasingly high degree. So all the way down here we have Horner's scheme applied to a 100th degree polynomial with a total of 200 floating point operations. Now remember when I started off I said, okay, most tools only work for benchmarks like with less than 40 floating point operations. So here this is 200. Yay, numerical fuzz is great. Okay, and we'll see here if we compare the results, the relative error bounds produced by numerical fuzz to the theoretical worst case relative error bounds, it's actually optimal. Okay, we wouldn't want it to be any smaller than this. And it would no longer be sound, but it matches those error bounds exactly. This is what I mean when I say that it's useful. All right, what about timing? So here we list the timing from numerical fuzz compared to these other tools. Timing is how long it takes for our type checker to infer an error bound. And you can see that even for this larger benchmark with 200 floating point operations, numerical fuzz produces an inferred error bound in 36 milliseconds. That's nice, it's fast. Great. All right, coming to my favorite table. So numerical fuzz scales to really large problems, and it's the only tool to generate relative error bounds at this scale. I think that's awesome. Okay, so here we have benchmarks of increasingly large size. Come down to the bottom one here, we have a matrix multiply between two 128 by 128 matrices, over 4 million operations. And we have our numerical fuzz bounds and our theoretical worst case relative error bounds. Again, open up a numerical analysis textbook, you will find those. We're within the same order of magnitude. Again, we wouldn't want it to be smaller than the theoretical worst case relative error bound because then it would be unsound. Our tool is not unsound, but it is useful. And then we're timing. Other than this last case, everything is under 10 seconds. Our last benchmark takes about 18 minutes. And so again, evidence for numerical fuzz being fast. Okay, so to summarize, our contribution is numerical fuzz. It's a functional programming language featuring a linear type system for rounding error analyses. It's sound, it's useful, and it's fast. It combines two key ingredients: a local error analysis, which tells us the rounding error produced locally by a function, with a sensitivity analysis, which tells us how functions amplify errors from inputs. And please see more details in our paper. I did not go into much detail in this talk due to time, but we have limitations to our system. That's important. We also have implementation details, a really cool metric semantics for our graded monad, and we also discuss how we can deal with things like overflow and exceptional values that occur during the evaluation of floating point programs. So thank you. That's it.
Questions? Hi, thanks for the talk, very impressive.
Yeah.
Do you have an idea or maybe already a characterization for what kinds of programs you actually nail the error bound for? Like you get the optimal?
Oh, beyond like polynomial evaluation. I mean, that seems to have like a very specific kind of pattern of computation where we're able to nail the error bound exactly. No, we don't have any like general result that says for programs with this specific kind of computation we will perform optimally. No.
Okay.
Yeah,
Cool.
interesting though. Thanks.
Would it make sense to apply numerical fuzz to itself?
To be honest, I'm not quite sure that I understand the question. So we write numerical fuzz programs. We write on type checker. Oh, I see what you're saying. Like, no.
Do you have any idea or examples of kinds of programs where the parameter C is not independent of the value that you're giving it, like that of the value of the input?
So are you talking about the function sensitivity part of this?
Yeah.
Is not independent, or is
Yeah,
it?
because here we are assuming that the amplification of the error is like independent of the value that we're giving as input to the function.
And sorry, to repeat the question you're asking, is there a case where we want it to be independent of the value or dependent on the value?
Dependent of the value.
Perhaps. I can't think of an instance where we would need that for numerical programs at the moment. Yeah. I mean, yeah.
Okay, thank you.
Mm-hmm.
Hi. So in terms of lots of fast implementations for transcendental functions, like inverse square root or sines, there's often like bit level manipulations or integer masks or whatnot. Would it be possible to extend this analysis to those types of functions? Is that already covered?
To transcendental functions and their implementations specifically?
Yeah. So
there are limitations of our language. Our metric semantics kind of limit the types of operations that we can handle. So in particular, I have a few like appendix slides here. So we are kind of, we're computing the relative error. And so really what's happening here is like you do not want you don't want x in this relative error example to be 0, right? And so numerical fuzz right now, it can't do subtraction. So we can do addition, and we can handle other, we can like do a square root, but for example, the implementations of transcendental functions, you need subtraction. But this is because we're focusing on a relative error analysis. So if we extended the language in the future, that might be possible.
Cool. Super cool. Thanks.
Yep.
In the polynomial example, what is considered the inputs for the purpose of these error bounds, x or
Oh.
the coefficients?
All of those things, the x and the values of the coefficients. Again, because it's a relative error analysis, we have to give bounds on the inputs for the other tools. Numerical fuzz, this is the bound generated for like assuming all values greater than 0, just positive real numbers. But for the other tools, we assume inputs of like 0.1, so 1/10 to 1,000.
Okay, and then follow up. This means, is the sensitivity analysis being reused for like multiplication, addition, over the both arguments and so forth?
So each of the floating point functions would have like its own sensitivity guarantee, and then it would be used inside of the function body of any benchmark that uses it.
Okay, and then so for the multivariable ones, does this become like a norm of a Jacobian?
So we didn't do a multivariable polynomial here. It's just Horner's scheme applied to like a single variate polynomial.
If
You're saying in the case that we did.
are an argument, right?
Yeah.
Then my multiplication sensitivity would have to involve an
The
error.
coefficient values are only used once, though. And so the sensitivity, like, it's kind of like a resource usage where we're saying, so like if we go back here, this function uses the value of x twice, and so it's too sensitive in this case to x. So if you imagine the case of like any of the polynomials, we're only one sensitive in each of the coefficients, but multi-sensitive in the use of the variable.
I guess maybe let me ask you this. A times x
Yep.
is what is its sensitivity?
One sensitive.
Okay.
Hi. It seems that this work doesn't support unbounded recursion. I wonder if it's easier to adapt this approach to unbounded recursion.
So we do not support recursion in numerical fuzz. So we have a higher order language, but we don't have general recursion.
I know there are some works about sensitivity analysis for unbounded recursion. So is there any challenges to extending this approach?
So I mean, in that case, you can imagine we might be able to give like a trivial bound to functions, like an infinite bound, right? But I'm not sure that it would be like informative for this particular application of a sensitivity analysis.
Okay, thank you.
Yeah.
Hi, thanks for the talk.
Yes.
A while ago, I read a paper that they used dynamic tracking to track the error of computations, and they found that a naive implementation of k-means would cluster things completely different based on rounding error alone.
Okay.
Would it be possible to extend your framework so that you could express this property in some way and improve your implementation of k-means as regards to error tracking?
Yeah, that's an interesting question. I think that it probably is possible, right? So the original application of the sensitivity analysis was for the fuzz programming language, right? And so there, I think they are able to like implement a k-means type algorithm. So I think that probably there could be some adjustment to the language to be able to deal with that sort of a problem. Yeah.
Okay, thank you.
Mm-hmm.
Hello, I have a question. How do you find the amplifier k, and what if the case that this k is does not exist?
Right, so if it's not a Lipschitz function, then we cannot give like a sensitivity bound to it. So the primitive operations in our language we prove on paper, like their sensitivity bounds and so on, and then this is guaranteed as it kind of is built up in our language.
In your work, it guarantees that this k can be found, right?
So any of the primitive operations of our language have to be shown to be k, like have such a k exist.
Okay,
Yeah.
thank you.
Mm-hmm. Done? Okay.
I think we're done. Let's thank Ariel again.
Yeah, Turner, what?
How? Hold up. Oh, is this why my talk at the Daphne workshop was all yellow?
Yes, exactly.
Oh.
Yeah.
Good, good, great.
Okay, our next speaker is Joe. And he'll talk to us about stream types. Take it away.
All right, great. Thank you. I'm Joe. I'm here today to talk about stream types. This is joint work with a whole bunch of people. Chris Watson, Emeka Nkrumah, Philip Hilliard, Harry Goldstein, Caleb Stanford, my advisor Benjamin Pierce. Without all of these folks, this would have fallen apart immediately. So I want to start this talk by answering a very simple question that in a lot of different scenarios has different answers. So I want to make sure we're all on the same page for what I'm talking about when I talk about stream processing. So I'm going to define stream processing by way of an analogy with an example. So here I've drawn a box labeled sum, and this sum box is a streaming program that's going to accept a stream of integers and produce the stream that is the running sum of the stream of integers that it gets in. Okay, so to illustrate, this program is going to get a 2, and then it's immediately going to spit out a 2, right? 2 is the running total of 2 and nothing else so far. And then we get a 1, and it's going to spit out a 3, right? 3 is 2 plus 1, the running total of everything it's seen so far, and so on and so forth. We get a 4, we spit out a 7, which is 2 plus 1 plus 4, etc. Okay? So a stream processing program is a program that behaves basically like this one. It's a program that maintains some internal state, that accepts an event from the outside world, updates its state, and spits out some output events in response. Okay? There's one other added piece of what stream processing programs are for the purposes of this talk, is that stream processing programs, the streams that I'm talking about, are going to be allowed to end. So there's going to be a single distinguished event in the grammar of what streams are called the end of stream marker. And when a stream processing program receives the end of stream marker, it can expect to no longer get any elements on that stream for the first, for the end of time. So when the sum box gets the end of stream marker, it's going to forward it along because anybody listening on the output should know that they're not going to get any elements as well. Okay? So once the end of stream marker has arrived, we can sort of take a step back and look at this whole computation in aggregate and really notice that over the course of the whole computation, what actually happened was when we transformed this input list, 214, to that output list, 234. So we really just, 237, excuse me. So what we really did was we took this input list and transformed it to the output list of partial sums of the input list. But the thing that differentiates the stream processing from list processing was the way that it happened over time, right? The inputs came in incrementally and the outputs were produced online as we went. So with that in mind, I'm going to give sort of a fun little definition for what stream processing is in this talk, and that stream processing is incremental list processing. Cool? Cool. How do I build a fancy little box like that sum box? There are a lot of different programming models available to you. The simplest one is to build a manual state machine. So more or less, you write a function of this type that takes the current state of your program as well as the latest input and then produces the updated state and the sequence of outputs you'd like to produce. Right? This is great because basically every single streaming program can be written as a function of more or less this type. Right? It's kind of like complete for stream processing. But the real issue with it is that it's very low level. You have to think about what are all of the possible states that my streaming program can be in, and if I'm in this state and I get this element, what state do I step to and what outputs do I produce? So in basically every part of computer science where stream processing is practiced, there exist streaming embedded domain-specific languages. You've probably seen one of these somewhere. A streaming embedded domain-specific language usually takes the form of a library that gives you a type like AlphaStream, and then a bunch of high-level combinators like map and filter and windowed operations and fold for which for you to write your programs with. And this is great. It's high level. It's familiar. It's straightforward. These are sort of inspired by list programming, etc. The main issue here is that if you have a program, say somewhere in your mind, and you'd like to get it out into code, but it doesn't nicely fit into this, these nice high-level combinators, it's really, really hard because you sort of have to cram the program that you have down into the combinators that you're given, and often that looks like just writing everything as one big fold, which, if you think about it for a moment, actually is no different than writing a state machine in the first place. Okay? What if you could just write list functions and have them run as streaming functions? So if you wanted to build that sum box that I showed before, what if you could just write this OCaml function that is the sort of partial sums function on a list of ints and have it run as a streaming function. I'm here today to tell you that you can with our new with our new language design, experimental language design called Delta. Delta presents to you a sort of general functional syntax of ordinary functional list programs. The main operations you get are nil, cons, pattern matching, general recursion. But the semantics of Delta is as streaming programs, right? So you get to write in this high-level functional list programming style, but you're not restricted to combinators, and you don't have to dive all the way down to folds when the program you're writing doesn't fit into your combinators. So at this point, oh yes, and of course, it has a streaming semantics, right? You write list programs, they run as streaming programs. At this point, you might be asking, like, how? This sounds very cool, but Joe, how do you do it? I'm a type systems guy by trade. That's how I grew up. We're going to use a type system to reject the list programs that don't have a nice streaming semantics. So to give an intuition for how this works, we're going to take a look at a list program that doesn't have a nice streaming interpretation. So here's the reverse function, as it would be written in Delta if I let you do that. Reverse takes x's, which is going to be a stream of s's. By the way, stream is written with the superscript star in Delta, kind of like regular expressions. We're going to pattern match on x's. If it's nil, we're going to return nil. If there's a head y and a tail y's, then we're going to reverse y's and then snock y onto the end of the reverse of y, snock being the reverse of cons, yeah? Right, so the problem, the problem here is that y, the head of the stream, arrives before y's, the tail of the stream, but then it's sent out all the way at the end, right? Head arrives before tail, the head has to get sent out after the tail is processed. So if you think about how this would have to run in a streaming fashion, you really have to buffer in the entire stream, flip it around in memory, and then start sending it out. And this is really not a nice streaming semantics, and we want to prevent this, okay? The core idea of Delta is to prevent situations like this one. If you get nothing else out of this talk, I hope you remember this slide. And the core idea behind Delta is that if all of the variables that appear in your program are used in order of the data that they're bound to's arrival, then the program is streamable with no memory, okay? So this core idea is the center of how Delta works, okay? So following this core idea, Delta is sort of stateless by default, but if you wanted to write a program like the reverse program, you can sort of selectively introduce state when necessary, okay? So if all variables are used in order of arrival, the program is streamable with no memory. So we formalized this idea, like I said, with a type system. The typing judgment of our type system looks like this. Read it as gamma proves E has type S, but think about it as E is a streaming program that accepts a streaming input structured like gamma and produces an output stream of type S. Okay? So E is the streaming program, takes input gamma, outputs S. The special sauce in our type system is the context gamma. In most presentations of most kinds of type systems, the context is just sort of a bag of variables. You can drop them, you can duplicate them, you can rearrange them, etc. In Delta, the context is actually a list where the order that variables appear matters. And in particular, the order that variables appear in the context describes exactly the order that the data for those variables will arrive at the program. So the first variable in the context gets bound to the first piece of data to arrive. And the last variable in the context gets bound to the last piece of data to arrive. Okay, let's take a look at some rules. Here's the variable rule. Type theoretically, it says that if somewhere in my context I have a variable of type S, then I can use it, and in fact, it has type S. But semantically, this says the following. So according to the context, the first thing we're going to get is data according to gamma. So gamma data is going to come in, and we're going to drop it on the floor. And then data of type S is going to come in, and we're going to forward it along. And then data of type gamma prime is going to come in, and we're going to drop that on the floor as well. So the variable rule says, use a variable, but semantically it behaves like pick out the substream of the input stream that corresponds to this variable, okay? How do we produce streams with multiple elements in them? Just like you produce lists with nil and cons, you produce streams with nil and cons in Delta. So the nil rule says that in any context at any time, I can say nil, and that has type S star is a stream of 0 or more S's. In particular, it's a stream of 0 S's. Semantically, this behaves as follows. As soon as we start getting any data on gamma, we're going to send out the end of stream marker and say, I'm done, you're not getting anything more from me. Okay? Here's the scariest rule we'll see in this talk, but it's also the most important, so I'm going to go through it the slowest. This rule says that if E is a stream program that produces an S, and E prime is a stream program that produces multiple S's, then econs E prime produces a stream of type S star, first by running E and then by running E prime. But the important thing is what happens here in the conclusion, the context and the conclusion of the rule. So in the context and the conclusion of the rule, we're required to split apart the context into two disjoint parts, gamma and delta, where gamma has to come before delta, and then gamma gets used to type E, and delta gets used to type E prime. So the early bits of the input get used to produce the first output, and the later bits of the input get used to produce the later bits of the later outputs. Okay? This is in a single rule what enforces the core idea. Variables are used in order because early inputs go to early outputs, later inputs go to later outputs. Semantically, it looks like this. We're going to get in some gamma data, we're going to run it through E, we're going to produce the first S, then we're going to start getting delta data, we're going to run it through E prime, we're going to produce the S star. Okay? So with these rules and a bunch of others, you can start to write programs. In particular, here's the program for stream filter. It looks just like the standard list filter function as you would write it in OCaml or Haskell or standard ML or whatever. You get a predicate on S's and stream X's of type S's, and you drop the elements that don't pass the predicate, you forward along the elements that do pass the predicate. It looks just like list filter, but it runs like stream filter. As soon as, when you run this in Delta, as soon as you get the first S, we're going to pass it through the predicate. If it passes the predicate, we're going to forward it along. If it doesn't pass the predicate, we're going to drop it on the floor. Okay? This is not like in OCaml or Haskell where you have to have the entire list in hand to start running the filter. Okay? The upshot of this part of the talk is that we can recover all of those standard list combinators in this style, right? You don't lose anything from your favorite streaming EDSL by using Delta. But that would be kind of a silly state of affairs if all I did for all of this work was just to get back to you can write in your streaming EDSL fashion. But wait, there's more. The ordered structure on our context generates this rich world of stream types that you couldn't possibly talk about in an existing stream processing language. So in particular, we have types like the concatenation type, where if S is a type of streams and T is a type of streams, then you can form the stream type S concat T, where a stream of that type looks like first a stream of type S, and then like a little marker that says we're switching over, and then a stream of type T. So if I'm producing one of these, I have to first send you a stream of type S, and then send you a stream of type T. And if I'm consuming it, first I get an S, then I get a T. We also have some types. A stream of type S plus T is either a stream of type S or a stream of type T, but first there's a bit that tells you, which way it's going to go. We have the singleton type of ints. A stream of type int is a stream on which you will only get one element, and that element has type int. We also have the empty stream type. If I'm receiving a stream of epsilon type, I will never get any elements. Okay? These types aren't just for show, although they are very pretty. They let us build stream programs compositionally where it's basically impossible to do so before. So to give an example, let's say I've got a light sensor somewhere in my house that's sending me a brightness signal every second. It says, there's 3 lumens of brightness, 5 lumens of brightness, 3 lumens of brightness, whatever. And I want to compute the average of each run when that number goes above 3. What do I mean by this? So we get a 2, 2 is not above 3, we're going to keep waiting. Aha, 4, that's above 3, we're going to start recording. 5, that's also above 3. 1, that drops down below 3. So we're going to then compute the average during the time that the number was above 3 and spit it out. Okay? 4.5, which is 4 plus 5 divided by 2. And we go back above 3, that's 6. We drop down below, and so we output 6, which was the average during the time that this run, the average of the run during the time that it was above 3. Make sense? Good? Great. If you wanted to write this in Apache Flink, which is a particular streaming EDSL that I will pick on for 5 seconds, you would have to write it like this. I don't intend for you to understand this, but basically the idea is that you have to write it all as one big fold, where you keep track of an option that says, am I currently on a run, and if I am on the run, here's what the length of it is, and here's what the running sum of it is so far. This is awful. It's not great to read, it's not great to write, it's generally not particularly nice. But in Delta, you get the types to help you think about the problem and hence structure the solution in a compositional way. You can write down types like int concat int star, which is the type of non-empty runs of ints. And then you can write down the type int concat int star star, which is the type of streams of non-empty runs of ints. And with these types and a little bit of programming wizardry, you can write a program like this, where you write a function average single, which computes the average of a single run by computing its sum, computing its length, and then dividing them. And then you can take that average run function and then map it over a stream of runs. Okay? The upshot of this is that it breaks down that operation into its sort of constituent parts, building these runs above, sort of filtering the stream for runs above 3 and then mapping an average operation over that stream of runs. But it has the exact same semantics as the fold-in flink. What happens is that as soon as the number goes above 3, this code will start computing the length of that run, the sum of that run, and then as soon as the run ends, it'll divide them. Okay? So it looks like this nice functional list code, but it runs semantically as streaming code. Okay, so in this talk, I've mostly told you about this cool, what you can do with Delta and basically how it works. The paper is mostly actually about the big heavy lift we had to do to get the type system and the semantics to work for all of this, which was quite a big challenge. So in the paper, you will find an operational semantics of the core calculus of Delta, meta theory, and a bunch of complicated proofs about the semantics and the soundness theorems. And then you might have noticed, by the way, that every single stream program I talked about in this talk had exactly one input and output, and that's not realistic at all. So we have a type called the parallel type, where streams of type S in parallel with T allow you to define streaming programs with multiple parallel inputs and outputs. And it turns out, to get the type theory to work out for this, you have to extend the type system where types aren't just lists. They're these sort of interesting tree things that borrows from a bunch of implication. There's a lot of really fun PL theory goodness in the paper. Okay? Future directions-wise, I've got a lot of stuff that I want to work on if you're interested in working on it. We want to compile this to various targets. We want to develop some case studies. There's a lot more theory to do. And if you out there in the audience or online, have an application that you think would benefit from Delta or Delta would benefit from, please let me know. My contact info is there. Thank you very much.
Hey, great talk. Thank you. So I guess my experience with streaming algorithms is that the hardest part is really, I know you have this design of stateless, but when you do need auxiliary state, like figuring out what that state is and incrementalizing it is a challenging problem. I was just wondering if you had any ideas of making that easier for programmers in the future. Then that's a first question.
Yeah.
The second one is do you think any of the ideas here can be extended to more incremental computation in general, like incremental compilation, for example, or whatever,
Yeah, great questions. So the first question, I do not have any thoughts on a better way of helping people figure out what the right bit of state is for their streaming computation. What I do have thoughts on is once you have what you think is the right bit of state, having your compiler help you ensure that you're using it correctly and that you're threading it around in the right way and not using it, holding on to it for longer than you want it to be, right? So we could talk offline about that. The second part, what was the second part? Just yell it because they heard it. Oh, yeah, okay. When I say incremental computation, I mean strictly monotonic incremental computation. So in some ways, this streaming as incremental list computation is kind of a restricted form of incremental computation. So I don't actually have much to say about the general case, where you can sort of, you can think about streaming as streams as an incremental data structure without retractions. But retractions are sort of generally allowed in incremental computation. So I'm not sure what to say about that. Thank you, though. Yeah, Lindsay.
Hey, Joe, great talk.
Thank you.
So I had a couple of questions that occurred to me. So one is, so you said, so in your language, a program it's well typed if it's streamable with zero memory. And of course, the first thing that occurred to me is, well, okay, what about a program that would be streamable with, let's say, 5 pieces of memory, right? So I know it would probably complicate your type system a lot, but I just wondered if you thought about what if you could say, okay, maybe maybe you want to reverse a list with 5 elements, right?
Yeah, this is a great question. So To be totally clear, the language design that we have does let you write programs with state. There's a thing that I didn't show that lets you sort of selectively say, I would like to store this piece of data in memory, and then I would like to send it back out now and manipulate it, and so like you can do that. In fact, we have not proved this. In an earlier version of the talk that you saw, we were talking about state in a different kind of way, where like, maybe you could sort of exactly capture the amount of state that a program uses by like reading it off the typing derivation. For very technical reasons, that theorem we can't quite prove yet for like basically proof theory reasons. But I am quite confident that a future version of Delta, you will be able to sort of press a button on the compiler and have it say like, please give my program a type error if I use more than order 1 space, or I use more than 6 words of space, or something like that. This is not a result of the paper, but it is something that like I'm pretty confident we can do, and I'd like to work on in future work.
Cool. Okay, and I just have one more question, and the question is, if a program is well typed in Delta, does that mean anything about how that program would benefit from lazy evaluation?
That's a great question, and there are deep connections between lazy evaluation and streaming, and I fundamentally do not understand laziness well enough to be able to answer those questions yet. But I'm working on it, and I know that there are some Haskell people around, and if they want to tell me exactly why what I did is just Haskell, like I would love to hear it.
Hey, you mentioned that you support multiple streams at the same time, and I was wondering if you had thought at all about streams that produce data at different rates. So I've worked with Lustre, which is another streaming language, and they have all these clocks and things kind of start getting complicated. So I was wondering if you had any ideas.
Yeah, so the model of sort of asynchronous streams or parallel streams that we have doesn't say anything about rates. Sort of. You can write down different types that basically say, here's a stream that sends sort of two ints, and this one sends 1 int, and then we step to the next, two ints on this output, 1 int on this output, and then 2 ints on this output, 1 int on this output. But it's done in a slightly different way than Lustre has, and the programming model for doing that kind of thing is not as nice. So I don't want to claim that we sort of supersede that, but you can write down types that kind of look like that kind of rate invariant, but it's sort of not a first-class citizen in our.
Thank you.
Thanks.
Hi. So my experience is that like the performance of stream processors is usually like pretty heavily dependent on like batching and like where exactly your yield points are and like pushback and things like that. And I'm wondering whether you've thought about that at all, either from like a type system or implementation perspective.
Sorry, can I ask are you talking about distributed setting, like cloud streaming, or are you talking about like Kafka or hardware or Kafka, or where are we on the stack?
I guess like a particular thing that I spent a long time working on is a thing that like gets data, like does some stuff with it in one process and sends it over TCP to another process, and like so on and so forth.
Sorry, I don't know why I asked. No, I don't know. These are things that we've had conversations about, but I don't have any concrete answers for you. Thanks.
Okay, so this has been fun, but in the interest of time, let's have one more question.
Thanks for the great talk. I'm curious just to get maybe one sense of one part of the programming model a little clearer.
Yeah, of course.
If you go back to the cons rule that you showed, it seems like it's enforcing more than just, I use the things that come first before I use the things that come later. If I wanted to have something that, doubled, repeated each element in a list.
Yes.
It didn't look like I could do that necessarily by just doing x, cons x, or cons f of x.
Yes, exactly. So this is precisely the memoryless condition that you get from just this type system, right? That disjointness means the disjointness between gamma and delta. It means that I cannot use, if I'm using an input in E, I can't use it in E prime, and so if I send something out, then it's gone, right? And if you want to send out X out twice, and then send out the next element twice, and then send out the next element twice, there's an explicit construct that we have in the language that lets you sort of pull a bit into sort of local state for a little while, use it, and then evict it.
Thanks.
So like that operation that goes from sort of S star to S concat S star that sort of does the sort of stuttering is you can write it, but you have to explicitly say so.
Thanks.
Okay, let's thank Joe again. And with that, the session is, next session will start at 4.
All right, everybody. Welcome to the most exciting session in all of PLDI, fast linear algebra. For those who saw the keynote this morning, I think you can expect the future of computing to be happening in this session. Kicking things off, we have Amanda, who's going to tell us about the combination of proofs in fast linear algebra. So please, Amanda, take it away.
Yes, for sure. Thank you for that introduction. I hope I live up to it. But yes, hello everyone. So today I'm going to be talking a little bit about our work on verifying the compiler of a functional tensor language. So for starters, low-level tensor programming often comes down to executing sequences of loop nests that compute over and storing into arrays. So just this example here is a small box blur program that, as its name might suggest, blurs an image. And you don't need to pay attention to the details, but just notice we have 2 loop nests in a row here. And the bodies compute by accessing into some arrays, and there are some if statements to make sure that those accesses are in bounds. So this is a pretty straightforward, simple program, about as simple as it gets, really. But there's already a number of common ways that you might want to optimize this. So for one thing, we can split one loop into 2 consecutive loops. And this way, one of these new loops doesn't need to have conditional statements guarding against executing in certain loop iterations anymore. But better yet, we can tile this computation now. And this increases locality and faster reuse of values produced in the first stage to the second stage. And we split these depth 2 nested loops into depth 4 nested loops to compute over these tiles. But oops, we forgot about the case where our tile size doesn't evenly divide our loop size. So we have to split out our loop ends here for each tile dimension to take care of those remainder loop iterations. And now the details of the optimizations aren't quite so important, but the takeaway here is that they're important and they are complicated. So writing each of these programs is tricky, to say the least. And in fact, I introduced at least one bug on each slide that I just walked us through, which is sadly kind of realistic when writing programs that require a lot of low-level tinkering. So even though handwriting these programs provides you maximum control over your optimizations, it's usually unsafe and error-prone. And that's not to mention extremely difficult normally to verify at this level of reasoning. We can get around this difficulty a bit by writing programs in a high-level language. So these languages can be functional and are often pure, strongly typed, and they have a reputation to be quite safe. I might be preaching to the choir here. And some high-level tensor compilers will even implement a number of optimization techniques in their lowering. However, these decisions are often black boxed by the compiler. Some compiler engineer decided to do this. And honestly, it can sometimes be a little bit inscrutable and just complicated in general. And often, it won't generate the exact code that you were hoping for. And so at this point, you end up sort of massaging your source code and try to coax your compiler into generating the code that you want. And while this process is safer, you sacrifice almost all control that you have over code gen to your compiler. And ultimately, verifying aggressively optimizing compilers is pretty difficult because of each optimization that's implemented. And that's why most aggressively optimizing compilers aren't verified and vice versa. So this is why in our previous work, we developed the tensor language ATL, a small program of it is shown here, with a 2-stage compiler. So we want to allow for source-to-source, high-level, user-level programmer optimization at this functional level up top here. And then a simpler, non-optimizing compiler that just generates the imperative code that the programmer wanted. And there's a missing link here because most low-level details that you need to make array code efficient aren't actually exposed in normal functional languages. So also as part of this previous work, we designed ATL with a special set of combinators that allow us to generate this performant array code. So you can see some keywords being thrown around here like truncate and flatten, but we'll discuss those later. All of this comprised our verified framework for optimizing tensor programs via these source level rewrites here. And this work included a trusted lowering algorithm to generate imperative loop nest code. And this was what was used to evaluate performance. And this was the state of the project as it was published back in 2022 at Popple. But for what we're going to talk about today, we verified this previously trusted lowering algorithm. And this actually led us to having to implement a new static well-formedness check to make sure input programs to the compiler satisfy certain correctness conditions. And these 2 new components here are the contribution of the work that we're going to be focusing on today. So ultimately, this lets us produce a fun little commutative diagram. But what this means is we can now achieve the performance that previously you had to get kind of by painstakingly writing low-level kernels. but now you get it with high-level ease and formal assurances of correctness. Now, every compiler is special, and each compiler verification effort is different because it has to contend with a number of different components. So these range from some old hat compiler problems that are common to most, if not all, compilers. But then there are some more particular and novel things that are specific to that compiler's architecture, or perhaps some features of its source language. Our verification efforts for ATL dealt with some of the items already featured on this already, but on top of those, we introduced two new concerns in proving correctness of our lowering algorithm. So storage index reordering and the introduction of garbage values, or what we call padding values. To begin, I'm going to focus on what storage index reordering is and how our proof had to accommodate this. So let's start by looking at a loop nest, a simple 2D loop nest here. The storage index we're concerned with appears at the bottom of the loop nest. This expression is a function of constants and the loop nest indices. So when most functional languages are compiled, the index expression here generated is strictly determined by the loop nest arrangement above it. Meaning, if a compiler wants to generate this loop nest, there's a good chance that it has to generate this storage index. And if we wanted to change this, if we're sort of like manhandling our kernel at a low level, we could kind of write whatever we want in this space, even if it's not memory safe. But if we're generating this code from a high-level language, there's no easy way to change it. There's no analogous component in your source code that you can change. So ATL addressed this by including a set of reshape operators, and these are combinators that represent common shape-related tensor operations. They'll look similar to some NumPy reshape operations if you're familiar with those, like transpose, flatten, truncate. And each reshape operator, you might notice, can be paired with another reshape operator that is essentially its inverse or its adjoint. So for example, truncation is the left inverse of padding, and splitting is the left inverse of flattening. And in fact, the rewrite framework that we implemented in previous work it can be used to introduce these reshape operators into programs via these verified equivalences. So if we start on the left with the two-stage program written in core ATL constructs we saw before, it's relatively similar to the blur program we saw. We can get the tiled program shown on the right here via these rewrites. And notably, truncate has to be introduced here. And that's the case in any tiled program where the tiling factor doesn't evenly divide the loop extent. And when compiled, these reshape operators specifically leave the loop nest structure alone and simply transform the generated storage index. So regarding how a reshape operator transforms a storage index, for each reshape operator, the compiler associates an index transformation. So for presentation's sake here, this is shown as a function of a flat two-dimensional index. And this transformation corresponds to the high-level tensor transformation that the reshape operator would be inducing on a tensor. We call these functions on the right-hand side reindexers for this reason. So for any given reshape operator R, the compiler associates a reindexer we'll call theta R. And here we look at how lowering treats reshape operators and how they affect storage order. So our call to lowering is going to include a reindexer argument here at the far right that is going to eventually construct the storage expression. The top level call to lowering is going to use the identity function. And now as the lowering algorithm proceeds, we expect this argument to be modified in subsequent calls to lowering. So here the program that's being compiled is a reshape operator R applied onto a two-dimensional tensor generation. So the lowering algorithm reduces this to the lowering of the inner program, but now with theta R as its reindexer argument. Finally, the lowered code uses the tensor generations present in this program to generate the compute order, meaning the loop nest structure here. So it's a loop of n and then a loop of m. And the default index here is determined by the loop ordering. So the default loop index is I times m plus j. And whatever index the reindexer produces from being applied onto this default index would appear here as the actual storage index that's generated in the code at the end. So what do we mean when we talk about correctness of this lowering algorithm? Or what do we expect, really? So we consider the lowering of any ATL program E. This lowered program is going to have to be lowered into, executed into a heap where the buffer X has already been allocated to store this output. And once it's been executed, it will produce the same heap, only with new values written into this space in memory. So how do we characterize what these new written values should be? Well, these newly written values must be the values of the original n-dimensional tensor that results from executing the ATL program E. Pretty standard to expect. The specific location where each of these values is written is dictated by theta, the reindexer that was passed down in lowering. And now this won't hold for any arbitrary reindexer we pass in for theta, because we have to enforce a well-formedness property on it to make sure that it's strong enough to ensure that lowering is correct, but weak enough to hold, since each step of lowering, as you saw before, modifies this reindexer operation, especially reshape operator. So how should we characterize this well-formedness of reindexers? Well, let's say we start with some tensor with some reshape operator applied to it, a reindexer theta that's going to write this reshaped tensor's memory values into memory, and we don't know anything about this theta besides the fact that it should also be well-formed. Then we expect this output should be the same as if we took the values of the original tensor and wrote its values into memory with the destination indices shuffled by the composition of theta and the reindexer theta r that corresponds to the reshape operator r here. And now with this characterization, we should be able to prove correctness of our lowering algorithm. But we're actually not quite out of the woods yet, unfortunately. We run into a problem pretty quickly when we try to prove this for two reshape operators, left and right truncation specifically. And that's unfortunate because I think we've established that truncation is pretty useful. It comes up when we tile almost anything. However, see what happens when we try to generate code with these reshape operators. So we look at an application of lowering onto the most basic program we could using truncation. This is truncation of a one-dimensional tensor generation. And again, proceeding with lowering, our reindexer becomes the left truncation reindexer. And as a reminder, the left truncation reindexer subtracts k from the storage index I. And so here it's being shown for the one-dimensional index. And we arrive at the following code. So you can see we're going to have out-of-bounds accesses into O for the first k iterations of this loop. The issue is a little less obvious with right truncation, but it's actually similar because it reduces the size of the dimension, and that appears as the stride in this index eventually. So generally, loop nest code generated with truncations is unsafe. We can address this by bringing the idea of padding values into this conversation. So the ATL language constructs left pad, right pad, and conditional guard, at least when P is false, all have something in common. They introduce filler values into a tensor, and this is padding. Padding exists to take up space in a tensor when we don't care so much about the exact value there. So there's no computation to specify what value it should take on. In ATL, it happens to be 0 because memory is 0 upon allocation. And as a result, this becomes at a low level an array entry that has never been written to after its allocation. And so why is this important in the case of truncation? Well, we can show how it's useful by fixing our problematic program. The simplest way is to insert a guard here that's true only for I greater than or equal to k. And we can see in the lowered program that there's now an if statement from this guard that protects this access here for the first k elements of this iteration. So now the first k elements are going to be uncomputed padding values. And this program is now safe because this if statement protects the access into O here. And you can play with this predicate a bit, and you can see it's still safe if you increase k, but not if you decrease it. And we can generalize this intuition here by noticing that truncation is safe so long as the values that are being truncated are always padding. And this is a semi-reasonable property to expect of our programs. If we recall that the point of introduction of reshape operators in a program are supposed to have stemmed from one of these adjoint pair rewrites. So we expect a truncate to sit outside of some equivalently padded program. To enforce this only truncating padding condition on programs, we need some way to track the padding pattern within a tensor. So we introduce what we call a pad type here, also called pi. So in the scalar case, the pad type is a single Boolean to say, is this padding or not? In the case of a non-zero ranked tensor, the pad type holds account of padding on both the left and right-hand sides, and recursively, the pad type of elements right inside the tensor after that, and the counts that these pad types apply to. Inference rules. We can statically infer the pad type of a program via a set of syntax-driven judgment rules to type ATL programs. And we can focus on the inference rules for truncation. You can see that they ensure that the amount to be truncated, here A, is less than or equal to the amount of padding found at the end of the tensor. So by proving soundness of this type system, we can show that a well-typed ATL program should uphold the safe truncation property as stated before and be able to be compiled safely. So to return to our two-stage compiler setup, this pad type checking is automated and integrated into our pipeline as a pre-compilation check before lowering is invoked. And we can include well-typedness as one of the correctness conditions for our statement then, and ultimately prove that our compilation strategy is correct. We evaluated this new pad type checking automation and verified lowering within the full compiler pipeline, meaning we use scheduling rewrites on a number of tensor programs to derive new optimized programs and apply this type checking and lowering to all of them. So what I'm showing here is each test program we used on the count of various reshape operators and tensor generations to try and convey a sense of program complexity that this is able to handle. And we chose these examples with an eye towards realism in terms of arrangement of reshape operators that would introduce and reshuffle padding patterns within a tensor. And we didn't evaluate this system for performance again, since the optimization derivation was tested in our previous work. But if you're curious about the performance capabilities of the system, I encourage you to read the previous paper. But with this work specifically, we can conclude that our verified compiler and type system is suitable for compiling a wide array of tensor programs and useful optimizations, with this new formal approach proving safety properties concerning index space reordering and padding. And thank you.
All right, please come up here to the middle for questions. And while we are waiting for our intrepid audience members to pop up, where's that square? How do I type that on the keyboard, that operator?
Where is that
like
square?
under the shift key somewhere? Or? No, actually, I mean, maybe more seriously, it's a really fantastic. I like this, and I really appreciate the interactive approach. I guess one thing with evaluation that's tricky, I mean, you showed the table, but how do you know that it's good enough? Like, you sort of have matched prior things, but like maybe if I wrote my tactics a little bit better, I could make the program a little bit faster. Like, what's the baseline?
Yeah, that's a good question. So if we're talking about evaluation for performance and not for expressivity here, there is, the idea is that you're not going to offload finding the optimally scheduled program on an automated LTAC sort of process to derive it. The idea with this whole thing is based on sort of user scheduling. So there is probably no, well, this is a generalization, but I would say there is no monolithic decision that can be made statically about what is going to be the most optimal scheduling decision at that point.
I guess what makes me nervous is, all the time I've spent in Theorem Provers, I have some goal left, so I know when I'm done. And here it's like, I just never stop, right? Just keep, there's not a QED at the end, but this is super nice. Any other questions? Okay, please make sure to find Amanda after the session. I think we'll go ahead and have Ari come and set up. Oh, and let's thank Amanda again. Very nicely done.
Oh, can you send me? Okay, great.
Fantastic. Okay, friends, please tune in again. We have another exciting talk, this time by Ari, on the D and Re composition, something about homomorphisms. This looks compelling. I don't know what it means, but let's tune in and find out together. Please, take it away.
Okay, thanks for the kind introduction. Yeah, right, my name is Ari. I'm from the University of Münster in Germany. And the next 10 to 15 minutes, I will try to encourage you to read our newest ACM top-class paper, which is actually generally saying about the general fundamental formalism for expressing and optimizing data per computations. So, yeah, right, before we start, just some quick introductory remarks. So, of course, this talk will very briefly highlight or actually advertise the main contribution that we are making in the paper. So I have, for example, like 20 slides to describe more than 70 pages, and I will focus on some illustrative examples rather than formal definition and details, which can all be found in the paper. I also want to mention that we have a full version of the paper uploaded on arXiv that contains really all the formal details, so that hopefully no questions are left open. And yeah, I must admit, the paper is quite long, so the top-class version is more than 70 pages, arXiv version even more than 130 pages. But despite the length, please, if you're interested in this topic, consider reading it. So we have many illustration and discussion, so even when skipping all the formal details, you should get at least general ideas here. And even more important than that, so this paper really tries to make a general fundamental contribution here to the community. So it helped me personally a lot to see things clearer, and I really put a lot of work in it so that it helps me, but hopefully also you guys. Okay, that one is. So okay, the goal of this work, so actually since I started my PhD, I always had questions in my head, so even when reading fantastic related approaches, so that still remains. So like for example, data parallelism. How can we define formally data parallelism? So we have all these different kinds of data parallel computation, let's say linear algebra routines, stencil computations, all these computations that are currently used in deep learning. We consider them all as data parallel, but often they are considered differently, expressed differently, optimized differently. And I was always wondering, what can be a formal definition where all these different kinds of data parallel computations can be are particular instances of this definition here. Yeah, so the next question. Okay, if we have such a definition, what are the basic building blocks that we need to express any kind of these kind of computation to these data parallels ones? So basic building blocks to express linear algebra routines as naturally as we can also express, for example, stencil computations here. And of course, we want these building blocks to be agnostic of hardware and optimization details, but still capture all information that are relevant for generating high-performing code. And the next question is, so how can we formally define optimizations for data parallel computation in general? So a general set of optimization rules that apply to any kind of data parallel computation here. Yeah, exactly. So general optimization here, that's already this question also, and the last one. Yeah, exactly. How can we structure these optimizations so that we can fully automatically explore the optimization space here? So for example, based on auto-tuning techniques. And yeah, this paper actually aims to answer all these questions fully formally. But okay, so let's dive in. So what this paper does is it introduces a formal framework for expressing and optimizing data parallel computations based on 3 major contributions. The first one is a high-level program representation. So as part of this contribution, we define data parallelism formally, and we introduce higher order functions for expressing data parallel computations, agnostic of hardware and optimization details, and still capture all the information that we require later in our code generation process to generate code that achieves performance even competitive to hand-optimized solutions here. The second contribution is introducing a formalism for expressing and reasoning explicitly about optimizations for data parallel computation. So actually, how can we make these problems smaller so that they fit into the memory and core hierarchies of state-of-the-art parallel architectures? And how can we generalize this optimization to apply to arbitrary combinations of data parallel computations and architectures? And the last contribution is, okay, we have an instance in our high-level representation. How can we fully automatically lower it to an instance in our low-level representation that's optimized for the device and also the data characteristics? So, okay, what are we going to do in the following? I will briefly just highlight and advertise our 3 main contributions. So the high-level representation, the low-level representation, and the lowering process. I will present some experimental results in terms of all performance, portability, and also productivity. Then briefly discuss related work and conclude the talk. Okay, at this point, I just want to emphasize again, so that will be actually in a very quite high level. So we have, for example, in our paper, an extensive set of experiments on more than 23 pages, while I just have 4 slides to describe the experiment. So if this talk can somehow gain your interest, the paper is much more exciting than the talk. So okay, our high-level representation. So while we have designed our high-level representation, we had 3 major goals in mind. It should be uniform, minimalistic, and structured. So here, uniform means it should be able to express any kind of data parallel computation without relying on any domain-specific building blocks. So we don't want to have building blocks just oriented toward linear algebra and some oriented maybe towards stencil computation. And if someone comes up with a new kind of data parallel computation, we need to extend and improve our language somehow. So we want to avoid this. We want it to be minimalistic, which means we want to rely on as less building blocks as possible to keep our language simple. Of course, for the user who uses the language, but also for us implementers. And we want it to be structured. So structured means here we want to avoid nestings and compositions of these building blocks as much as possible to further contribute to the usability of our, or to the simplicity of our language. Again, for the user and also for us implementers. And the paper we can show that our high-level representation first defines data bulk computations as the so-called multidimensional homomorphisms that were mentioned. And it expresses data bulk computations using exactly 3 simply composed higher-order functions only. So we only need these 3 functions that you can see there on the top, infu and deum on outfu, to express any kind of data bulk computation according to our definition. So here, just quickly, infu is responsible for the input data. So it expresses what kind of input data are used, how they are accessed, these kind of things. And deum always and uniformly expresses the data per computation part, and outfu is responsible for the output data. And the paper we could show, just using these 3 patterns, we can express a wide range of data per computation. Like, for example, linear algebra routines, where it express dot products, matrix vector multiplication, matrix multiplication, batch matrix multiplication. And yeah, actually, we could even show in the paper that these expressions naturally evolve from each other. So, for example, a matrix vector multiplication, nothing else than computing multiple dot products. That's exactly reflected in our formalism here. The same for matrix multiplication and matrix vector multiplication, and so on and so forth. But we have also, for example, expressed convolution-like stencils, Jacobi stencils, which differ significantly from linear algebra routines, because they access neighboring elements in their input, so they are often quite differently optimized than linear algebra routines. Then we have also expressed maximum bottom box sum, which was a running example in the PLDI paper. We have scan patterns, map-reduce patterns, histograms, probabilistic record linkage, which is used in data mining to identify duplicate entries. So there's really a wide range, and these also, in these computations, really define major characteristics here. So regarding our low-level representation, so just on one slide quickly. So the goals have been, we want to express in hardware and data optimized decomposition and recomposition of data per computations. So as I said at the beginning, how can we make the problem smaller, that it fits into the memory and core hierarchy of the architecture? No matter what architecture, we have an abstraction for architectures introduced in our paper here. And the second goal is it should be straightforwardly transformable to executable program code. So for example, OpenMP for CPU, CUDA for GPU, OpenCL for multiple kinds of architectures. And straightforwardly actually means that all the major optimization decisions are already expressed in our representation. Just that you get a quick idea how it looks like, the low-level representation there. So these are just 3 phases. On the right side, you can see the decomposition, so how we make the problem smaller. In each step, we say how we assign these smaller computations to the core memory hierarchy. Then we have below what we call scalar computation, so that's usually the inherently sequential part of a computation, and then we recompose the results back. Okay, just a quick excursion. So based on the structured design of our low-level representation, we could even show that we can visualize optimizations. So we have these kind of visualizations for any kind of data per computation, and also for any kind of architecture. They are of this form. I don't want to dive into detail here, but I just wanted to mention it. And yeah, just one quick slide about code generation. So code generation is actually not the focus of our paper here, but we have outlined it in the appendix of the full version of the paper, actually. And it's based on an imperative-style pseudocode notation, and it's intended actually to be described in detail in our future work. So what I just want to say, so of course we have implemented everything, but it's not that much described in the paper and can be found in the appendix of the full version. So regarding our lowering process, our lowering process from high level to low level is based on formally defined performance critical parameters, so that we get a structured optimization process that allows fully automatic exploration of the space. So in this case, for exploration, we use auto-tuning, particularly our auto-tuning framework ATF that we have presented a couple of years ago at TACO. And so our parameters don't aim to introduce some advanced new optimization here, but to unify, generalize, and combine well-proven optimization. So data movements, tiling, makes them flexible, and generalize them to apply to arbitrary data per computations here. And yeah, regarding experimental results, so we really try to make experimenting challenging for us. So we evaluate our approach in terms of performance, portability, and productivity. We try to compare to the best available solutions right now. So like, for example, Apache TVM, which is a scheduling-based approach, polyhedral compilers, PPCG for GPU, Pluto for CPU, the popular Lift approach, which is based on functional concepts, and also we compare to domain-specific libraries like NVIDIA QBLAST, QDNN for GPU, and 1MCAL and 1DNN for CPU. And these are highly optimized libraries by hand at the assembly level to achieve the highest performance on their target architecture. And we also consider a bunch of different case studies here. So we have linear algebra routines, matrix multiplication, matrix vector multiplication. We have two different kinds of stencil computations, a 1D example, Jacobi, and a 2D example, Gaussian convolution. We have an example from quantum chemistry. We have this data mining example. And we also have a deep learning case study inside the experiment. And yeah, so regarding our performance elevation, so these are just some highlights, and just for the deep learning case study, because that was the most challenging study for us, because most of the competitors are highly optimized for them. So for example, TVM is highly optimized for deep learning, and even the vendor libraries. And the performance evaluation is based on a runtime comparison. And here we can observe, for example, we achieve speedups of more than 2x as compared to TVM, and sometimes even more than 9x as compared to the hand-optimized solutions here. We have some slowdowns as compared to TVM, but these are actually mostly for a technical reason. So our implementation currently uses the NVRTC library, while TVM uses NVCC. I have no idea why NVRTC generates less efficient CUDA assembly than NVCC, but that's the reason for slowdowns as compared to TVM. So the portability evaluation in our paper is based on the so-called Pennycook matrix. So here a value close to 0 means low portability, and a value close to 1 means high portability. So for a deep learning case study, we can see that we achieve higher portability than TVM in all cases. And actually also as compared to the other approaches, which achieves the lowest portability of 0 only. That's because they are limited to particular architectures maybe, or with particular application classes. So they're not even functional portable, and that's especially not performance portable. But in the paper, we also consider just portability on GPU, CPU to make comparison for these approaches easier to us. But that's not on the slides. And yeah, the productivity evaluation is just based on intuitive argumentation in our paper. So classical code metrics like lines of code and COCOMO efforts are not very meaningful for these short and concise programs as we use, and of course also the related approaches here. So regarding related work, so we could show in the paper that MDH often achieves higher performance, portability, and productivity. So we have a big discussion about that in the paper. So for example, we could show that scheduling approaches usually achieve very high performance, but they often struggle with achieving portability and productivity. So productivity mostly because they incorporate the user into the optimization process. So there must be optimizations expressed explicitly. In contrast, polyidal compilers often usually achieve very high productivity, even by optimizing fully automatically straightforward sequential code, but therefore they struggle with performance and portability. So we have a big discussion what are the reasons for this and that. I just want to briefly highlight this here on the slide. And yeah, that actually brings me to the conclusion. So the conclusion is very short here. So the two big giveaways I want to give you, so it's NG is the formalism for expressing and optimizing data per computation in general here. And that we could show that MDH achieves higher performance, portability, and productivity. So it's not just formal stuff, it really has some relevance for practice here. And yeah, I also want to use this opportunity to make some advertisement for our website. So we have recently uploaded the website. Please feel free to check if that's somehow interesting for you. And yeah, that's actually the end of my talk. So thank you very much for listening. I'm grateful for any kind of feedback, because this work is very important for us. So it can also be bad feedback, so that's fine. And yeah, I'm happy to answer questions now. We should have plenty of time left. Thank you.
Yeah, as already mentioned, we have time for questions. So if folks could use the mic there in the middle.
Hey, thanks for the talk. So it went by a little quick for me, but I would be very interested on your results for understanding in which cases you outperformed 1DNN, 1API, cuDNN, those sort of vendor-supplied libraries, and why specifically did you outperform in terms of like the optimization of that application?
Okay. So first of all, nothing was there cherry-picked. So these were all that I presented here, sizes used in real-world deep learning neural networks, so that for sure. The reason why we exactly outperform them, we cannot explain always with certainty, because they are not open source. But one reason is we can auto-tune, for example, our code specifically for the input size. While these approaches rely on heuristics that are optimized toward average high performance over a range of sizes, we think that that might be the reason that we achieve better performance than them. But you cannot check inside, but I think that...
Is that size tuning consistent with all the results you've seen, or I guess it is not a way
there was
to
no
test
pattern
that
in it. Sometimes we were
hypothesis,
better,
really?
sometimes not. And we have a very thorough comparison. So for example, with QBLAS, we compared to all the QBLAS routines using all the algorithm stuff. We compared also to MKLJIT and these kind of things. That can be all checked in the paper. But it's mostly because of the auto-tuning, I think. These approaches, of course, they hand-optimized libraries, so the vendor libraries don't have this auto-tuning overhead that we have. But particularly for applications like deep learning, where the same implementations are reused, this auto-tuning time is usually mostly amortized.
Okay.
So it's worth it.
Thanks.
But you have this auto-tuning overhead, of course. Yeah, thank you.
Thanks. I look forward for reading the 130-page version.
That was my goal.
In the meantime, I wanted to ask, what would you identify as like the remaining open challenges?
Okay, so that's just, we see this as a starting point in this direction. So we have a lot of things to do. We cannot express sparse computations. We currently just target individual data per computation. So when we have, for example, a deep learning graph where we have multiple data per computations, we currently cannot optimize across the computations. There are a lot of things, so there's still much things to do, but I think these are all extensions, not improvements. So that's a fundamental that we need to do all these things.
Okay, thanks.
Thank you.
I had one last question, maybe, unless folks have another one. What's the penny cook method, or what was it? That's the portability metric.
It was presented as the one SC workshop that people are currently using. So that's a metric that you can measure performance portability. How performance portable is the code? So when you write just one code, so if you have a value close to 1, then you can expect that on different kinds of architectures, you usually will achieve, let's say, 90% of the peak performance, for example. And if the value is lower, then sometimes you might perform good, but often also worse. So it's some formula, it's also in the paper, that compares to the best solution you have observed and also to other kinds of measurements that you made. So to get to these, so how otherwise would you assess performance portability?
So, and so what's the formula over? What are the variables? Like, do you just run it on several platforms and look at how different the performance is, or is there just a quick intuition for that?
To the approach that you have observed the best performance. Sometimes these were often the vendor libraries, the number of architectures. I have the formula not in mind right now, I must admit. I just wrote it all once down, computed it, and used it. So I'm no expert for this, but it seems to be well accepted, at least by some people. Okay.
Yeah. Okay, let's thank Ari again.
Thank you.
All right. Up next, Olivia is going to tell us about compiling sparse workspaces. This is not about WeWork or something. This is the computing version. So please, Olivia, take it away.
Thank you. Hi, everyone. My name is Olivia. I'm from Stanford University, and I'm presenting on behalf of Gengan Zhang, who could not make it here today. So today, I will be talking about supporting sparse result tensors by way of sparse temporary tensors, or workspaces as we call it, through the compilation of modular and general sparse workspaces. So I've given this slide many times, but there are many sparse computations in the world that we may care about, and they show up in many real-world application domains like machine learning, scientific computing, data analytics, and more. And to address these applications, a lot of research has focused on compiling sparse tensor algebra codes. And a large part of this work has studied how to iterate over sparse tensors. So for example, here I show an inner product sparse matrix multiplication, and it's inner product because the contraction dimension is at the innermost loop. And much of this work has focused on the compilation of what we call sparse iteration theory. So it's a lowering algorithm on how you can support an expression or the right-hand side. But this is limited by the actual fixed algorithm. And so what I mean by that is when I say inner product, it's the loop nest that we show. Because a small change in the code, like the one I show here, now I'm showing a row-wise sparse matrix multiplication where I just interchanged one loop. And then a simple loop interchange requires new research ideas. So in order to support this, we needed to introduce a framework for loop reordering and also needed to introduce dense workspaces. And moreover, there's been work, so the bolded tensors are compressed and they're sparse, and there's been research focused on how to represent these compressed data structures for inputs only. Notice that A is not bolded. But again, with another small tweak, one loop interchange, we're now at the outer product sparse matrix multiplication algorithm. And this body of work doesn't know how to handle this, which I will explain later why. And then in the dense world, though, this change would be trivial for functionality. So maybe not for performance, but at least for functionality and for code generation. And then further, if we wanted to generate a sparse result tensor, again, now A is bolded, prior compilation methods also cannot do this. And they can do this in a trivial way, which is you compute the dense result and then recompress it, but they can't do it on the fly. And the reason why is because of what we call sparse scattering. So here I will show a sparse matrix multiplication example for outer product on specific tensor values. And all the boxes in white are supposed to be 0, and all the boxes in gray have non-zero elements. And one important feature to note for some background is that by a compressed result tensor or a sparse output tensor, this means that the data structure does not have random insert capabilities. And I'll show why. So let's consider the first iteration of our outer product sparse matrix multiplication. We're iterating through the K loop or the outermost loop. So we're going to get these two input vectors from B and C. And then we're going to take these elements from B and C because they're the only elements in our vector. And I show the partial result or the partial sum matrix slice above. And then this partial result will actually be inserted into our compressed result tensor as shown. And we call this element insertion because you can, in fact, insert this element into your compressed data structure since it's currently in order. So there's no problems. So on our next iteration at the k=1 loop, we're going to take the next vector slices on our input, and we're going to go through the first element. And the first element will produce a result, but notice through our slices that there is now a collision. So 0.6 and 0.3 need to be added together, and we're going to call this element deduplication. And likewise, when we go to the next element in our k=1 iteration, we're again going to produce an element. And this is still OK, because we're still appending to the compressed result tensor. However, a problem occurs when we go to our last iteration for this specific example. The 0.2 and the 0.1 and 1.0 are multiplied on our inputs, but it produces an element that actually comes before, in order, the elements that we previously computed. And so what has to happen is we have to shift our compressed tensors over, insert the element here, and then change a bunch of the data structure. And actually, we can't do this efficiently, and oftentimes compilers don't know how to generate code for this. So one solution to handle this case, this out-of-order insertion, is through temporary tensors or workspaces. And in this case, you can insert a temporary tensor that has all of the elements as coordinate points that are then sorted, and then you can build your compressed result from there. And more generally here, I show the symbolic loop nest equation for this outer product sparse matrix multiplication to show that a workspace needs to be inserted. So our workspace is this Wij. And then we also still need to generate the iteration for this workspace code. And conceptually, Wij should be able to be any data structure possible, whether it be dense or sparse, so compressed. But in practice, that's not the case. Prior work has only shown theory for dense workspaces, and they've shown theory for higher order dense workspaces, but they only have implementations for one-dimensional workspaces. And the problem with that is that our dense workspace has the asymptotic memory of the shape of the dense tensor. And so what this means is that when we run performance benchmarks or memory footprints of this sparse matrix multiplication outer product, we often get an out-of-memory error for certain data types, or for certain input data, excuse me. In the case of a sparse workspace, we can store it as a compressed tensor, and then this has the memory footprint of proportional to the number of non-zeros, and then actually this allows us to run more, enables us to run on more input data. And likewise, it's important for a compiler to handle both types of data structures because actually, in some cases with the data, a dense workspace might be better, and in other cases, a sparse workspace might be better. And again, many prior sparse workspace algorithms do exist in the literature, but these are for fixed function, and they're often handwritten. And so the issue with that is that they're not general. So no algorithm is able to actually be used for a compiler approach. And so since generality is the challenge, because we need to be able to, in our compilers, support a wide array of algorithms, and like I mentioned, support a wide array of data structures, both on the input tensor and in our workspace tensor. So to solve this, we actually introduce a compilation system. And the new features of our compiler are shown here in orange, and today I will only talk about two parts. I'll give a brief overview on our insert, sort, merge algorithm template and our insert, sort, merge function calls. For information on the rest of the new compiler features, please take a look at our full paper. So what exactly is the insert, sort, merge algorithm template? Our ISM algorithm is an algorithmic backbone. So what I mean by that is that it actually has we define an API with compress replacing the workspace iteration, and an insert, sort, and merge call replacing our building of our workspace. And this is done via this function API that then users define at runtime. So what do we mean by WAC and WALL? So these are workspace memory pools called the accumulation array and the all array. We insert elements via the insert function into our accumulation array until it is full. And then we sort elements from the accumulation array into the all array, and then we merge them together. And then finally, at the end of everything, we take our all array and then we compress it to our result tensor. So as an example, taking our running example, I'm going to show you how the algorithm works. At our first k equals 0 iteration, we're going to go through the insert phase. So the insert phase, again, taking these two input vectors, will produce this coordinate point shown in our accumulation array. Then on the next iteration, we're again going to insert our elements into our accumulation array. But now the accumulation array is full because it has a size of 2. So we're going to go into our sort phase and our merge phase. Upon sorting, in this example, there's no sorting because the points were already sorted. So we skip that and we merge it into our all array. And then we keep moving forward. So now we're going to insert the elements again into our accumulation array, insert the final element into the accumulation array. In this case, they're unsorted. So we're going to enter, it's still full, we're going to enter the sort phase. And then once it's sorted, we're going to actually be done with our computation and merge it into our final all array. At the end of the computation, we're going to take the all array, which is done, and then we're going to compress it into our final result. And this is because even though our workspace is sparse, the data structure is still not necessarily the same compressed data structure that the user may want. And even though our insert, sort, merge algorithm is an algorithm template, well, we need to actually figure out what exactly should be in those function calls. I mentioned previously that they're user-defined, but what algorithm is exactly important, what's performant, what's better for memory footprint, and so this is something that we explore. In our work, we provide two different concrete policy implementations, and we define a policy as actually what the user defines in their insert, sort, merge, compress functions at runtime. And so the first policy that we introduce, you don't have to understand this diagram, is the coordinate sort policy. So from a high level, the coordinate sort policy takes these input elements, again as coordinate points, and just sorts like a canonical coordinate list. The next policy that we implement is a bucket sort policy, and this bucket sort policy takes some function given our coordinates and then produces some value key, and then that key is used to then bucket the elements. And so this allows you to bucket elements and then sort faster. And in this case, I show the key where the key is actually just the first coordinate in your matrix. And the interesting part about our ISM algorithm template is that we're able to express the existing algorithms I showed as a categorization and breakdown of our interfaces. So here I show Gustafson's algorithm for one-dimensional dense workspaces. The insort policy for Gustafson's algorithm is a one-dimensional coordinate list and a flag list along the J dimension. And deduplication happens actually when you try and insert your coordinates when a flag bit is set to true. The sort is the same as the bucket sort that I previously described, and then the merge algorithm is Boolean indexing based on your flag, and that's how you merge. And then likewise, we're able to categorize existing algorithms into our insert, sort, merge API as well. And the key insight here is that sparse workspace algorithms actually fit into this pattern because this is the pattern needed to actually build your sparse workspace as shown in the example. So this interface is, in fact, enough. And the sparse workspace, for evaluation of our compiler, we show memory savings of, on average, 3.6 times the amount of memory for matrices that do not out-of-memory error on a 256 gigabyte machine. So here I show, again, our expression for the outer product, sparse matrix multiplication, and show the memory savings when the dense workspace does, in fact, run. But our sparse workspace approach actually enables a larger range of input data as well. And I don't have graphs for this, but I also want to say that the compiler benefits from supporting both sparse and dense workspaces because the sparse workspace on runtime can be up to 27 times faster than the dense workspace in prior work. But on the other hand, dense workspaces can also be up to 7 times faster. So the compiler should support both. And then likewise, we do an evaluation on our concrete policies and show that they do, in fact, matter for runtime. So here I show an evaluation for sparse MTTKRP with the expression shown down below, and we test 3 of the policies in our paper. So the first policy is bucket, which is a bucket sort policy. The second concrete policy we have is still that same bucket sort policy, but with a hash function instead of the original key with the outer index function that I described previously. And then the last concrete policy we have is the coordinate sort that I explained previously. And what we do is we sweep the J dimension of our sparse MTTKRP, and we show that, in fact, in some cases, the coordinate concrete policy is better, in some cases, the hash function is better, and in some cases, the naive bucket sort is better. And so the key insight is that no policy dominates, so you really want a compiler that is able to handle all of these policies and all of these algorithms through user-defined runtime function calls. In conclusion, our work enables sparse temporary tensors or workspaces as a first-class concept for tensor algebra compilation. Our work generates modular and general sparse workspaces through code composition at runtime and compilation, respectively. We provide several concrete sparse workspace policies and provide a categorization for prior work sparse workspace algorithms. And we have future work on supporting parallel sparse workspace code. Thank you so much.
All right, friends, if you have questions, please come up here to the center.
Hello. Thanks for the nice presentation. I have actually 2 questions. The first one is very quick.
Yes.
So in Taco, then, the workspaces are mostly dense. Am I right?
In Taco, there's a difference between the theory and the implementation. Like I said, the theory is on higher order dense tensor workspaces, so the paper is published on that. The implementation, in fact, can only support one-dimensional sparse workspaces.
Sparse workers.
Or no, sorry, one-dimensional vector dense workspaces.
Okay.
Sorry.
The second question, is the implementation available for this work or not?
We do not have an artifact evaluation, but you can send me an email and I will, yeah. We can.
Thank you very much.
Hi, thank you for the presentation, very nice. I have a clarification question. The experiments were in what context? GPU, multi-cores,
So they were all sequential code on CPU.
Sequential code, okay, thank you. And you show like, 3 different policies about how to introduce this optimization. How do you choose between them? Is the user, or is a sort of auto-tuning, or it's a dynamic policy by which you select one or the other?
Yeah, that's a great question. So we make it user-defined, and we just take, like, our compiler just takes the user-provided code. So the user would have to implement all of these policies and then run all of their code, and then they would get the result. And then we envision an auto-tuning framework to sit on top of this compiler. Thank you.
Hi, great talk. So with some of the examples that you showed and walked us through, it looked like it was using like a CSF or a CSR style of compression. Does this format support, or would you consider generalizing it to support other compression formats?
Yeah, that's a great question. So we are able to recompress using the theory from the 2018 formats paper. At UPSLA, I think. So based on that 2018 paper, we're able to generate code from COO to any other compressed level format. Again, there's a difference in theory and implementation. In theory, they create a wide range of level formats for more complex compressed data structures. But in actuality, in the implementation, they only show it for dense, sparse, and singleton levels. And so we are only able to generate code for the same types of levels. But the theory should exist for the other data structures.
Got it. Thank you.
All right, let's thank Olivia again. Fantastic talk.
Great.
All right, so wrapping up this session, Bastian is going to tell us about a safe GPU systems programming language, which I suspect is going to give us both safety and control, which was set as the target this morning. So yeah, this is fantastic. All right, take it away.
Yeah, thank you. I'm going to present some work that I did together with Michael Stoiber, who is here today, and Sergey Gorlach. And basically, computing on GPUs is great. We heard today in the keynote that we need to use GPUs if we really want to get the performance out of our system, and we want to do this, and GPUs offer us tons of parallelism, thousands of threads that we can use, and are being used for high-performance programming in many fields now, medical imaging, scientific computing, and of course machine learning, just as some examples. The thing about computing on GPUs is that GPU programming is too hard, at least that's what I'm claiming. And so when we program GPUs, usually we use a programming model like CUDA, for example, which is very low level, inherits a lot of the problems that C and C++ have. Programmers have to manage their threads manually, have to manage memory accesses manually. And this way, it's easy to introduce bugs and, for example, data races. So for example, when you write a CUDA program for the GPU, you write a kernel function. This is a function describing a transposition on a two-dimensional matrix. We read the matrix in and write it out in a transposed form. And this kernel function is executed by thousands of threads. It's pretty much copied onto all the threads, and all the threads run it independently. Threads on the GPU are organized into multi-dimensional blocks. And these blocks are then again organized into a multi-dimensional grid. Then each block and each thread can be indexed or uniquely identified in every dimension. And we can use these indices for explicit indexing to determine where each thread accesses the memory. The problem about this is that when we want to reason about whether this code is correct or whether we have introduced a data race, we kind of need to build up a mental model about the memory we are accessing and the grid that we have currently running this function on. So here, for example, if we write into the temporary array, which we assume is a 4x4 array, and then we assume that our grid is simply a single block of 2x4 threads, then in order to figure out whether our code is correct, we first need to figure out or substitute all the identifiers or the indices in our expression to figure out where each thread accesses the memory. So in this case, for example, the first row of our threads in the block is accessing and writing to a different memory location without a problem. But when we do the same for the second row of our block, then we see that some threads in the second row write into the first row of our array and create a data race, which then leads to undefined behavior, so we have to avoid this. In this case, the problem simply is that we forgot some parentheses. We can reintroduce them, and then every thread is writing to a different memory location, and we don't have a data race anymore. But in a larger program, this kind of bug can be quite hard to find and to debug. So our question is, how can we create a safe GPU programming language? And our answer to that is Descent, a safe GPU systems programming language with a philosophy similar to Rust, that if the program successfully compiles, it should be free of data races and other memory problems. If we look at the same transpose program for the GPU in Descent, the first thing we notice is that the function that describes the transposition is annotated with a grid. And in this case, we have an explicit annotation with a two-dimensional grid of 64 by 64 blocks, and then for each block, 32 by 8 threads. This means in Descent that this entire function is collectively executed by the entire grid. And then within this function, we describe how the entire grid collectively executes the function. So for that, we use the scheduling instruction in line 6, for example, where we say that for each block in the y and the x dimensions, so both dimensions of the grid, we want to schedule some computation. And then in the body of the schedule, we say the same thing again for the threads in the block in this case. So then when we are in the innermost body, where we describe what each thread does, we can use normal instructions for the threads. We can write and read from memory and to memory. For example, in line 14, the threads are accessing and writing into the output array. And here we make sure in this line that each thread has to write into a different memory location. And we do this by using views and that by them describing how each thread or which memory locations each thread has access to and which memory locations it owns. So for this example, for this line, for example, we again can assume that our output array is simply a 4x4 array. And we now want to distribute the memory locations that form a tile in our array over all the blocks. So the first thing we do is we apply a view. And this view reshapes our array into a 4-dimensional array consisting of 2 rows, and each row contains 2 tiles. And now we can simply distribute these tiles over all our 2-dimensional block, or over our 2-dimensional grid. I'm writing here block 1, 1 to say that the block at index 1 and 1 is accessing the tile in the bottom right corner, but in reality, we would write simply block, meaning that all the blocks are going to take ownership over one of the tiles. So here, block 1, 1 takes ownership over the tile at index 1 in the row with index 1. And after the block has taken ownership, the block has full access to it. But since we usually want to read and write with threads, we also need to describe within the block the elements that each thread takes ownership over. So we do a similar thing again. We apply another view, group by row. We group the elements together that each thread should own, and then we take ownership with each thread. So here again, for example, the thread with indices 0 and 1 would take the group of elements at index 1 within the row at index 0. Now, the threads have separate access to separate memory locations and are allowed to safely read and write to and from memory. And this is how Descent's extended ownership model ensures that memory is accessed safely via views. In Descent, there exist 5 basic view primitives: map, group, transpose, reverse, and take. And these pretty much only allow us to somehow partition our memory or permute the memory locations so that it's guaranteed to always be safe. And we can then use these basic view primitives to compose more complex views. For example, the group by tile view is simply a composition of a map group followed by a map transpose. And then views are composed to express these kind of complex memory access patterns. Going back to the transpose example in Descent, we now understand that in line 9 here, the threads write safely into the TMP memory because we first group the memory locations, and then each thread takes ownership over a different group of memory locations. And then down here in line 15, we also see that, again, each thread now reads safely from each memory location. Or do they? Because in this case, if we type check our program with descent, we get an error message which says that there's a conflicting memory access. And the reason for that is that in line 9 before, we distributed the ownership of the memory locations in TMP over the threads using the view group by row. But in line 15 now, we are trying to redistribute the ownership using a different view, in this case, a composition of transpose and group by row. Which means that in theory, and in this case it would be the case, different threads would be reading and writing, or possibly reading and writing at the same time, creating a data race again. So the problem here is that after taking the ownership in line 9, we need to release the ownership again to allow renewing or redistributing a new version of the ownership. And we do this by simply introducing a synchronization over the entire block. And this synchronization then for each block releases all the ownerships that threads have taken within the block, so that after this synchronization within the block, each thread can distribute ownership again anew. And this way, descent ensures that there are no data races. But descent does a couple more things that we describe in the paper. So we also make sure that we respect the separated memories between CPU and the different GPU memories. The assumptions between CPU and GPU code must match, which we make sure of. Safe memory accesses and branching code must also work, of course. It's quite important for a lot of applications. And then we make sure that there's an absence of barrier divergence, which would also lead to undefined behavior, for example. What we did then is we formalized the type system and we implemented a compiler that translates descent programs into CUDA programs. And we used this compiler to evaluate how performant our approach is. So how easy is it to generate performant CUDA code? And to figure this out, we chose a couple of common benchmarks from different sources with some interesting characteristics that we describe in the paper. Here we show a graph where we show the median relative performance on two different GPUs that we measured. And in green we have the CUDA versions, the reference versions, which always have a performance of 1. And then the descent version, if the bar is higher, it's faster, and if it's lower, it's slower. And we see pretty much that programs generated from descent achieve competitive performance to handwritten CUDA. The gem version is kind of an outlier, and the reason for this is that the CUDA version that we are comparing to has done complete loop unrolling on all the loops for the gem, and our generated code generates just loops with static loop bounds, and then we let the CUDA compiler decide, and the CUDA compiler just does a better job at unrolling, and this way our implementation here is faster. But pretty much we are still similarly fast. The same reason goes for Jacobi SVD. One interesting point that I wanted to make is that we can talk about atomic read, modify, write operations, for example, which is why we did the histogram benchmark, for which read, modify, write operations are quite important. And it's nice to see this is very similar to how you use atomic read, modify, write in Rust. And we can simply introduce it here as well. Then additionally, there are still some domains that are quite hard to express. As I have shown, we are pretty much partitioning our data statically, but there are definitely domains where partitioning the data statically is not that easy, especially graph algorithms. So we looked at the single source shortest path graph algorithm, and the implementation we looked at is highly optimized, uses thousands of lines of code, exploits the weak memory model of CUDA, all things that we can currently not express in this way in descent yet. So we introduced simply an unsafe escape hatch, which allows us two things. First of all, we can easily interface with external CUDA code. And additionally, sometimes we need to, even in descent itself, we need to access graph data with dynamic indexing, which is again difficult because we don't have the static partitioning anymore. So that means we use the unsafe in this example to implement the algorithm and then reuse, for example, the existing work list implementation that uses the weak memory model and these kind of things. This way, the unsafe code provides us with a quick method of interfacing with existing CUDA code and integrating more and more CUDA code into Descent. To conclude, Descent assists programmers in managing CPU and GPU memory and enforcing previously implicit assumptions. Descent extends the concept of ownership to the thread hierarchy and uses views to ensure safe memory accesses on the GPU. And the evaluation shows that Descent is expressive enough to write programs that achieve performance on par with handwritten CUDA code. We have created a website, descentlang.org, where you can find a link to the paper, a link to a document with the type system formalization, and a link to the GitHub project with the compiler implementation. Thank you.
Okay, if there's any questions, please feel free to step up to the mic in the center. One thing I was curious about, how is the type system imprecise? Like, are there places where the type system, like what kinds of programs is the type system going to reject that are actually okay?
Yeah, for example, if you have indexing with dynamic indices that you need for graph algorithms, for example, then we don't know into which partition the index wants to go, so we kind of cannot express these kind of programs yet. Yeah.
And I guess maybe the flip side of that, were there any interesting bugs that this caught for you while you were building your evaluation?
You mean
like a favorite mistake that you made that if you'd been writing it in CUDA would have gotten through, but Descend kept you safe?
Simply forgetting synchronizations. I mean, barrier synchronizations are easily forgotten. Yeah.
Very nice talk. Thank you very much. How general, or what are the limits of the views that you can compute?
Mm-hmm.
Are they limited to essentially blocking an array, or you can support something more general like taking the diagonal blocks of an array?
Ah, interesting.
Because this appears, for example, in an NW and also in LUD, where you descend the computation, so you have a block slice.
Mm-hmm.
Are you able to support those benchmarks?
Great question. So I think taking like a diagonal is definitely possible. It's a combination of the views and how we select which thread accesses which element. So basically the take can throw away data, and then you would have to do a bit of work to explain how or which data should be thrown away by each thread, like in every row, or which. Actually, we have, sorry, one of the Jacobi SVD, I think, does something in that direction at least. That you take ownership over a row, but you basically need only one memory location from that row. And you can do that with, you distribute the ownership over several threads, and then each thread accesses exactly the element on the diagonal, for example. But they're probably, I'm happy to talk about it further.
Yeah, let's take it offline.
Yeah.
There's time.
So in comparison to Descend, to the traditional way of writing a CUDA program, you would have your host side code where you would specify essentially the grid dimensions that you encode in your types. And the separation between that and the kernel is so that the kernels are generic-ish over the launch parameters that you would specify. And now I'm wondering, like, two sides of this. One is, since now that you're effectively adding this extra information into the kernels themselves, could you, one, perform other optimizations since you know the entire shapes of these blocks, the dimensions that normally CUDA programs have at runtime only? And second, does this limit the, could you go even further in the type system and say, let's add parameters in certain ways, and like, would that work? How would that limit, would that exacerbate the imprecision problem? Like, could you speculate on that, on both sides of that?
So one, I think so. Currently, the translation to CUDA code is very straightforward, but I'm definitely interested into looking into more optimizations, and I definitely think, yes, the extra information should help us in optimizing. The second question I didn't fully understand.
Oh, about parameterizing these kernels themselves? Would that be possible? Would that introduce
okay.
different unforeseen challenges?
You mean parameterizing, for example, the block sizes and these kind of things?
For example,
yes.
sure.
I think it introduces additional challenges for sure, but I'm very interested in that. I have some ideas on how to approach that already. Yeah.
Yep, sounds great. Thank you.
So what are the reasons you made a new language for this? Can you infer everything from like CUDA code?
You mean can I mean I can already express everything in CUDA. I agree, but yeah, the main reason is that when I write CUDA code, it's very easy to make mistakes, and I want the compiler to help me out and tell me when I made a mistake. That's the reason. Okay.
Thank you for the talk.
Thank you.
Did you consider using separation logic to define the semantic of your programming language? Because it doesn't, by skimming your paper, it doesn't look like you did.
Yeah, I mean, not when we started, but by now I'm at the point where I'm thinking, yes, that would be very interesting. Actually, we don't have a formal definition of the semantics yet, so that's definitely a very interesting approach for me to go towards that, yeah. Thank you.
All right, let's thank Bastian and all the speakers from the session one more time. And that concludes everything in the Sweden room for the day. Please make sure to check out posters. There's going to be a lot of fun discussion there. And see you all soon.